So thank you, everyone. And before we proceed for our first invited speaker for the first session, Professor Sabriya Madam from Edge University, Turkey, I would like to give you a brief introduction of this event of the initiative by IUPAC, that is Global Women Breakfast of 2025. So celebrating women in sciences across the countries and throughout the world. So this was an initiative taken up by IUPAC. And what is the goal behind this? What was the initiative? What was the basic concept behind this? So I would like to detail you before, and after that one promotional video will be shared to you of IUPAC GWB Women Breakfast. And as we all know that IUPAC, or more or less we all are not so much unaware of this word, because in the school times, during the school duration, all of us have remembered and learned this IUPAC nomenclature, though we are from the chemistry or we are not from the chemistry, but most of the students are familiar because they go through this chemical sciences throughout their secondary school education, and we know that IUPAC. So the first, I would like to proceed that the prime goal of the GWB series, that is Global Women Breakfast series, is to establish an active network of people of all genders to overcome the barriers to gender equality in science and discuss in groups about the recent barriers and prospects for accelerating equity in science and thereby fulfilling the sustainable development goals. As we all know, that SDG, Sustainable Development Goal of United Nations, that is goal number 5 and goal number 10. So now the question arises, why we are celebrating every year the GWB Global Women Breakfast in the month of February only, not only here in India, but throughout the world. So as we know that the International Day of Women and Girls in Science is celebrated on 11th of February every year to promote the equal access and participation in science for women and girls, to recognize their importance and their important role play in STEM. And STEM means science, technology, engineering, and mathematics. So what we call STEM, they are the STEM fields. And the basic objective of which include the sum of the pointers, that is empowerment of women and girls, to contribute to the achievement of the 2030 Agenda for Sustainable Development, to recognize to the women contribution in STEM and catalyzing inclusivity, equity, and diversity in sciences, to encourage more girls for their career in science, and to bring the fresh perspectives and creativity to research in sciences. So if we see the back history, a significant gender gap has persisted throughout the years, at all the levels of STEM disciplines. Now, not only in India, but all over the world. So even though women have made tremendous progress towards increasing their participation in higher education, but they are still underrepresented in these fields. So gender equality has always been a core issue for the United Nations, and the empowerment of women and girls will make a crucial contribution not only to the economic development of the world, but also definitely to progress across all the goals and targets of the 2030 Agenda for Sustainable Development, that is SDG as well. Also, we can observe that over the last few decades, the world's understanding of climate change has improved exponentially due to the dedication of some of the world's top women climate scientists who championed the science behind the climate change. And hence, a shift in the structure and culture of science in workplace is urgently needed. So as a woman, women's advance in their scientific careers, the gender gap continues to widen. So the proportion of women in research, management, and senior positions remains disproportionately very low. And in cutting edge fields of AI, we can see only 22% are women, that is 1 woman in 5 women. So despite a shortage of skills in most of the technological fields during the industries, women still account for only 28% graduates in sciences. So this is a very low figure we can observe. And women and girls represent half of the world's population, and therefore also half of its potential throughout the world. So today, only 1 in the 3 scientists is a woman. Therefore, lack of gender equality limits the scientific progress and hamstrings a country's development and its efforts to build peaceful societies. So for the first time, the IUPAC president, Professor Mary Garson, you will see in the promotional video in the next step of this event, that is Professor Mary Garson, asked a question of celebrating the Nobel Prize winner Madame Marie Curie on the centenary of her Nobel Prize in Chemistry for her keen contributions and marvelous achievements. Not only achievement as a woman, but also achievement as a scientist and achievement as a chemist in the field of chemistry and chemical sciences, which will be further shown to you in the promotional video, in the upcoming video of IPSC GWB 2025. And moreover, we cannot forget the contribution of Professor Hind, Dr. Hind Al-Abdei, in memory of her, which stands GWB 2025. And as Dr. Hind was an influential leader in chemistry, a dedicated researcher, and a tireless advocate for equity, diversity, and inclusion in STEM, so her contributions are particularly in advancing opportunities for women in chemistry, and this have had a profound impact on the chemical community. So the aim of the International Year of Chemistry, which was celebrated during 2011 IYC, was also for chemists. That is, to connect and participate and create a chemical handshake around the globe. And now with GWB networking event of women sharing a chemical moment in time. So being a chemist, let us move for the chemical handshake. And in this sequence, I would like to request Dr. Rashmi Verma ma'am, Head of the Department of Chemistry, CVRU, to please share the IUPAC promotional video. And let's have a chemical handshake in this platform of Dr. C.V. University celebrating IUPAC GWB. Rashmi ma'am, please share the promotional.
Yes, ma'am.
Okay.
It is in process, ma'am. We are sharing.
Sure. You will know the basic concept which I have already briefed you, and it will show you some images also, as well as you can see the meaning has been incorporated in the down bottom side in Hindi also.
Welcome everyone to IUPAC Global Women's Breakfast, GWB 2025, where we are accelerating equity in science. You are part of a network of more than 30,000 people overcoming barriers to gender equality in science, technology, engineering, and maths. Your efforts also support the UN Sustainable Development Goals, gender equality, and reduced inequalities. If this is the first time joining the GWB, you may be wondering how this all got started. The GWB founder, Professor Mary Garson, asked, "How can we celebrate Marie Curie on the centenary of her Nobel Prize in Chemistry, the IYC, and connect groups in support of women scientists?" Her idea was simply breakfast. Having breakfast together is a great way to network. To take networking one step further, she encouraged groups to interact with each other and create a handshake that traveled around the world.
My idea was quite simple. Women know how and when to network. They go out to breakfast. And to take networking one step further, I encouraged groups to interact with each other using social media, and in this way, we created a handshake that travelled around the globe.
The first global breakfast was an amazing success, with roughly 5,000 participants at 100 events in 40 countries, a community of organizations in support of women in chemistry. In 2019, the Global Breakfast returned as part of the centenary of the International Union of Pure and Applied Chemistry and the International Year of the Periodic Table, with over 10,000 participants at 200 events in 50 countries. The Global Breakfast is now an event that happens on a single day each year. The first events begin in New Zealand, progressing around the globe, ending in Hawaii. The influence of the GWB has grown over the years with an increasing number of events and participating countries. In 2025, the GWB will have hosted more than 2,000 total events in 100 countries. And the GWB is an official event of the International Year of Quantum Science and Technology. Advances in quantum technology will be crucial to achieving many of the UN Sustainable Development Goals. This year, we have challenged you to create inspiring videos in support of GWB and IYQ and post them on your favorite social media platforms. Check out the details on the website. Don't worry, you can still submit your videos through March 31st for another round of awards. Here are the videos selected for today's welcome.
Science and technology have the power to change the world, but only when everyone gets a seat at the table. Imagine a future where diversity and equity drive innovation, where science truly reflects the creativity and brilliance of all people.
We hope that you are inspired to make a difference where you are today. What are some things that you can do? Take time today to celebrate successes and achievements. Inspire the next generation to pursue careers in science. Support efforts to close the gender gap in science. Most importantly, reach out and make a connection with other GWB groups to see how you can accelerate progress together. A great way to connect with other groups later this year is to attend the IUPAC World Chemistry Congress happening in Kuala Lumpur, Malaysia this July. Find out more at IUPAC2025.org. We thank everyone for hosting a breakfast event today. Your efforts are critical to achieving a brighter future. Thank you also to our wonderful sponsors, Royal Society of Chemistry, Bayer, American Chemical Society, De Gruyter, and Royal Australian Chemical Institute. Please plan to join us again next year for GWB 2026, happening February 10th. Have fun today and enjoy your breakfast.
Thank you, ma'am. Thank you for sharing this video. And before we proceed, I would like to also congratulate Ganguly sir from Nagpur, from President of and Secretary of Association of Chemistry Teachers. He have also collaborated with us, and for through his guidance also, we have got this particular initiative of IUPAC. And welcome, sir, Ganguly sir. And also, I would like to let you know, not only this year, we have also celebrated our International Year of Periodic Sciences, IYPT, in the year 2019. And that was also a global initiative by the Department of Chemistry of Dr. C.V. Raman University. And after that, this is the year, International Year of Quantum Sciences, and will move accordingly with various initiatives of the Department of Chemistry of Dr. C.V. Raman University. And now, Dr. Rashmi Verma, over to you to continue further. You're not audible, ma'am.
Yes, I'm audible, ma'am.
Yes, right now.
Thank you so much, ma'am. Good afternoon, everyone. I'm audible, ma'am. Good afternoon, everyone, and welcome to the International E-Seminar to celebrate IUPAC GWP Global Women Breakfast 2025 on recent advances in chemical sciences. It's my pleasure to welcome you all to this prestigious event, which has brought together renowned expert researchers and scholars from around the world to share their knowledge and insight on latest development of chemical sciences. I would like to extend a special welcome to our keynote speakers, our respected Vice Chancellor Ma'am and Professor of Chemistry Dr. Jayati Chatterjee Mitra Madam, Dean Faculty of Science Dr. A.K. Srivastava Sir, Professor Department of Chemistry Namita Bharadwaj Madam, Associate Professor Department of Chemistry Dr. Milan Hep Sir, Associate Professor Department of Chemistry Dr. Rakesh Kumar Yadav Sir, Assistant Professor, Department of Chemistry, Dr. Abhishek Sharma sir. Assistant Professor, Department of Chemistry, Dr. Vinita Tambrakar, Dr. Mr. Jay Prakash Sahu, all the scholars and all the students. To all, to our participants, I welcome you to this interactive and engaging platform where you will have the opportunity to learn from the expert, ask questions, and share your experiences and perspective. This e-seminar is a treatment to the power of collaboration and knowledge sharing in advancing the field of chemical sciences. We hope that discussion and interaction that take place today will inspire new ideas, foster new connection, and pave the way of future breakthrough. Before we begin, I would like to introduce our eminent expert, keynote speaker. So, first keynote speaker is Professor Sabriya Yusan, Professor Institute of Nuclear Sciences, Age University, Turkey. Welcome, ma'am. Dr. Jhuma Ganguly, Associate Professor, Department of Chemistry, Indian Institute of Engineering, Science and Technology, IIEST, Shibpur, West Bengal, India. Welcome, Jhuma, ma'am. Dr. Rachna Ghimire, Associate Professor, Tribhuvan University, Kathmandu, Nepal. Dr. Ananya Baksi, Assistant Professor, Department of Chemistry, Jadavpur University, Kolkata. Welcome, Rachna ma'am. Welcome, Ananya ma'am. And also, I would like to share dear now for proceeding further, I am sharing the attached tribute slide to all Canadian institutes participating in 2025 Global Women Breakfast. Dr. Hind Al Abdullah, who was influencer leader in Canadian chemistry, a dedicated researcher and tireless advocate for equity, diversity, and inclusion. So, this slide is shared according to IUPAC guideline in memory of Professor Hind Al Abdullah. The global chemistry community mourns the passing of Professor Hind Abdullah on January 10, 25, a leader in environmental physical chemistry. She tackled critical issues in air quality, atmospheric aerosol chemistry, and geochemistry, earning numerous accolades, including L'Oreal's 2023 Hoffman Little Award and 2021 University Researcher Professor Award. Beyond her research, Dr. Abdullah was a dedicated advocate for equity, diversity, and inclusion within the Canadian chemistry community. She was an inaugural member of CSC Working Group of Inclusion, Diversity and Equity wide, contributed to making chemistry inclusive and played a key role in advancing equity initiative. Her passion, uh, her passion, data-driven approach, and leadership left a lasting impact on both sciences and academic community. Uh, the information is that we lost her in this January 1025. So this is tribute to her work in this GWP 2025 IUPAC event. Thank you. Now, um, ma'am, this is the time for session one.
Okay, no issues, ma'am. Let's have a chemical handshake. And with all the participants, all our speakers, and all the chemical community, that's the main reason, Women in Sciences with chemical handshake. So to start the first session, you can call our respected first.
Yes, ma'am. Sabriya, ma'am, are you there?
Yes, I am here.
Good afternoon, ma'am.
Good afternoon.
How are you, ma'am?
Thank you. I am fine. First of all, I would like to start my expression, my gratitude for the opportunity to
Welcome,
present
ma'am.
at this meeting. Thank you for your invitation. It's
Namaskar.
really very special, make a presentation, very make, like, how can I say, a special day for women, for all.
So how's the climate in Turkey right now?
Yeah. Thank you. Um,
So now I would like to introduce Dr. Sabriya Yusan.
okay.
Can I, ma'am, introduce yourself? Okay.
I will
Prof.
share or you will share my presentation. Which
Then go through our brief profile, ma'am.
Your brief profile, ma'am, for the participant, information for participants. Professor Dr. Sabriya Yusan is academic staff of Age University Institute of Nuclear Sciences. At the same time, she is director of Institute of Nuclear Sciences. She graduated from Celal Bayar University, Faculty of Arts and Sciences, Department of Chemistry. She completed her master's degree in analytical chemistry at the same university, Asher. She did her doctorate at Age University, Institute of Nuclear Sciences, and postdoctorate at Ganguly University, Nepal. She is currently working as a professor at
Ma'am, your network is unstable, I think.
there is a connection to
No issues, ma'am. You can continue. I would like to welcome you further for the session, for your insights for our participants, your knowledge, sharing your knowledge, and your very keen deliberation every participant is waiting for. Welcome, ma'am.
Thank you. Uh, I I will share.
Hello, ma'am, can I audible? I'm
Ma'am,
audible.
ma'am, your network was unstable, so I have invited madam to just for her deliberation.
So it is needed to read the brief biography,
Okay,
ma'am.
it's okay. You started, initiated, but the network was unstable. So our participants are waiting. So I have welcomed her. She'll continue her session.
Okay.
Mute your mic, ma'am. Sabriya, ma'am, we need to share your screen or you can share from there.
Uh, I think you can share. No
You can
problem. Yes,
share.
I
Okay.
I can.
Okay, sure, sure. Okay, ma'am. Just a minute. We are sharing within 2 minutes, ma'am.
Okay.
Madam, we are sharing PPT very soon. We are sharing PPT, ma'am, shortly.
We are also having Professor Santosh Kumar Sar sir with us from BIT. Welcome, sir. Welcome in this session.
Good evening, Professor.
Good evening, sir. Good evening. Madam is here with us. Our session is just about to start, sir.
Hello, Professor.
The session is just about to start.
Fine.
Yes, sir. Welcome, sir.
Okay.
Good morning. Good morning, sir.
Good morning.
The introductory session is over. Now the first session.
PPT is on screen, ma'am. Madam, please proceed, ma'am.
Hello, Professor.
Hello.
Yes, ma'am. The screen is visible to you?
Okay, I think I can start.
Yes, ma'am. It's visible
Okay.
to you. The screen is visible to you.
Yeah, it's okay. I can see.
Okay.
Sure.
Yes, thank you again for your invitation. My talk is about recent advance in chemical science. I believe women scientists are really very valuable contributions to, especially in chemical science. Because of that, today I will talk recent advance in chemical science. Sometime I will focus on my studies with my group. Then I will finish my presentation. Yes, next please. Yes, as you know, chemistry is a fundamental to modern advancements across various fields, driving innovation in healthcare, energy, technology, and environmental sustainability. I and my group also working on studies focused on environmental studies especially. As a result, the application and development of chemistry garnered significant social attention. However, the production and use of chemical products often present challenges such as inefficient raw material utilization, low yield, complex process, and generation of numerous byproducts. One of the most pressing concerns is the release of toxic and corrosive pollutants and waste, which exist in various forms across different media. Poisoning serious risk to both environment and human health. Addressing these challenges has become imperative and leading to the emergence of green chemistry. You know, the green chemistry is the most popular topic now in the world, I can say. People are trying to find less they want to use less chemicals to synthesize their materials or their absorption or the other synthesis procedures. Now they are focused on green chemistry. I will also talk about the green chemistry. At its core, green chemistry aims to optimize material and energy efficiency in chemical reactions while minimizing pollutant generation, ultimately enabling more sustainable and environmentally friendly production. Yes, the other slide, please. Yes, here are some key areas where chemistry is really important. One is healthcare and medicine. Under this title, We can talk about pharmaceuticals, personalized medicine, biomaterials. Pharmaceuticals are really very important because chemistry is essential in drug discovery and development, leading to new medications for diseases like cancer, Alzheimer's, and infectious disease. Especially in my institute, one of the groups is studying with pharmaceuticals. They are using radionuclides, labeled radionuclides for leading to new medications for cancer and Alzheimer's, especially. And the other parameter topic is energy and sustainability. We can talk about renewable energy, battery technology, and carbon capture and climate solutions. Chemistry all contributes and helps to develop methods for carbon dioxide capture, conservation, and sustainable materials. Also, chemistry contributes to development of efficient solar cells, fuel cells, and biofuels. The other subject, battery technology, like lithium-ion solid state and alternative batteries. They are all about chemistry. Yes, the other slide. Yes, the other is nanotechnology and material science. I think this topic is the base of the most of the studies. Because when you use nanotechnology and material science, you can use your materials for every area. For example, catalyzers, adsorbents, or maybe the other sections. I think the base of the science is this section. In this section, advanced materials, smart coatings, and graphene materials is the most popular subject. Advanced materials like superconductors, nanomaterials, and polymers. Smart coatings, they have self-cleaning, antimicrobial, and super hydrophobic surface. Graphene materials, it is also the popular subject, especially in my studies. Innovations in carbon-based materials are leading to ultra-fast electronics and lightweight composites. Graphene-based materials also very high surface area, and because of that, we are using these materials for our studies, especially removal of the radionuclides like uranium, thorium, strontium, or cesium, the other radionuclides. We are using this material mostly. We are modifying this graphene also with the other natural biopolymers or the other metal organic framers. We are modifying them, we are preparing, synthesizing them, nanocomposites with graphene oxide. Yes, the other. Yes, agriculture and food science. I think chemistry is everywhere. Agriculture and food science, we can talk about fertilizers and pesticides, food preservation and synthetic biology. Chemical innovations increase crop yields and pest resistance while reducing environmental impact. Chemistry enhances food safety through better preservation and packing materials. Scientific biology, genetically engineered microbes produce like food additives biofuels, and even lab-grown meat. Yes. Environmental protection, yes, green chemistry, water purification, and biodegradable polymers. Under this section, we can talk about green chemistry. The green chemistry focuses on sustainable processes that minimize waste and reduce hazardous substances. Water purification, chemical technologies improve water treatment through desalination, filtration, and maybe absorption process to remove pollutants from the water. Chemistry enables the development of eco-friendly plastics to combat pollution. You know, this is the, again, most popular topic nowadays. Microplastics, yes. Okay. The other is space exploration and defense. Chemistry advanced fuel efficiency in rocket propulsion and spacecraft materials. Again, chemical resource is critical for oxygen regeneration and water recycling and food production in space. And materials chemistry helps in developing shielding for astronauts against cosmic radiation. You can see chemistry continues to be at the heart of scientific and technological progress, shaping the future of industries and everyday life. Yes. Now, I say sustainable chemistry and technologies. Now I will talk about this subject and what is the recent advance about this subject. For example, rare earth metal cycling, green photocatalysts. These photocatalysts are now using recently green adsorbents, artificial intelligence in chemical research, advanced materials and nanochemistry like boryl radicide, cloth materials, and fluid chemistry and nanoenzymes. Yes, you can change. Yes, rare earth metal recycling. This is a very important subject because we know the rare earth elements are very valuable and we are using in many industries. Because of that, we should find the most best extraction methods for these metals. Nowadays, ionic liquids are mostly using for this aim. You know, rare metals are generally separated from their natural ores by solvent extraction. However, since urban mines have different metals, and it's really very difficult to separate them. Especially in my country, we have thorium ore, and rare elements are together with thorium, but it's really very difficult to separate them, thorium and the other elements. Because of that, recently, ionic liquids, which are molten salts at room temperature, have attracted considerable attention since they are novel, environmentally friendly solvents. Yes. You can see the ionic liquids. These ionic liquids can contribute briefly to the development of novel and highly efficient separation process for rare earth elements, metal elements. After the studies, they found that use of the success separation process depends on the use of extraction, like suitable for ionic liquids. Because the selectivity and extraction ability for the target rare elements are should be known, and it can be used with this aim. So you should choose the best ionic liquid for your aim. Which rare elements do you want to separate, cerium or lanthanum or the others? And so recently most of the scientists are using these ionic liquids. Also, two or 3 years ago, we used this ionic liquids for extraction of the rare elements in our study. But they are maybe disadvantage is they are a little expensive. Yes, we can change the slide. The other subject is green photocatalysis, especially development of eco-friendly catalysts from agricultural residues. I will talk about green chemistry. Yes, green chemistry. If you want to use green chemistry, you have to use really minimum solvent and maximum natural products, like for green catalysts, now using agricultural residues. These green photocatalysts are facilitate chemical reactions, using light energy while minimizing environmental impact. These catalysts are typically synthesized from agricultural residues like rice husk, sugar cane bagasse, or corn stalks. How they work? Green photocatalysts harness solar energy to drive reactions, such as water spilling for hydrogen production. This process helps in environmental remediation and contributes to sustainable energy solutions. What is the advantage of these materials? Renewable and biodegradable source reduce reliance on toxic and rare metals. They are cost-effective compared to traditional photocatalysts, and they reduce the waste by upcycling and upcycling of agricultural products. You can see the picture. One synthesis method is chemical route, the other is plant extracted mediate route. The chemical route, we are using more chemicals like hydrazine, sodium borhydrate, ascorbic acid, and the others. But in green chemistry method, you can use agricultural residue. Yes. Listen. Yes, I thought catalyze. As you know, these catalysts play an indispensable role in chemical reactions, accelerating reaction rate and reducing byproduct formation. However, some traditional catalysts harmful substance, like I said, chemical load, and byproduct during reactions, reducing yield. Thus, the development and use of green catalysts have become a key approach to realizing green chemistry. This is environmentally friendly approach, and they minimize using chemicals and reduce byproduct generation. Yes, we can change. Green catalyzed synthesis is often complex and costly, particularly for advanced materials like metal organic frameworks and nanomaterials. Ensuring catalyzed recyclability, stability, and durability remains difficult, as seen in platinum-based fuel cells are leads to performance decline. Scaling up production poses additional obstacles such as cost, material processability, and environmental costs. Important. Future research should focus on improving catalyst design, synthesis, and efficiency while reducing costs, leveraging technologies like artificial intelligence for optimization and enhancing recycling methods to minimize resource waste. Yes, the other slide, please. Yes, for bioremediation, what we are working on for especially application environmental remediation. Green technologies also play a very crucial role in environmental remediation by reducing pollution, conserving resources, and promoting sustainable development. For bioremediation, you have to use microorganisms, fungi, or plants to detoxify the contaminated environment. For example, bacteria used for this bioremediation for the heavy metal or pesticide removal. Soil remediation, plants like sunflowers and willows absorb toxins from contaminated soil and water. Green adsorbents, how they are worked. We use natural or engineered materials to trap pollution from the water, air, or soil. Especially biochars from agriculture waste are using. They remove heavy metals or the other pollutants like organic or inorganic contaminants from water. The other adsorbents like zeolites or clay-based adsorbents, they are also using in wastewater treatment and air purification, especially because they really have a very high surface area and pore volume, so their ability is very high for removal of pollutants, heavy metals, or the other metals, right? Like radionuclides. We are also using mostly zeolites and clay-based adsorbents. Yes, we can continue. Yes, I say green adsorbents. They are the most important maybe parameter is cost effective. They are cost effective, low cost and high absorption capacity. Sustainable and renewable materials they are, and they are non-toxic, mostly biodegradable material, low energy input, and minimal waste. They produce minimal waste. And also the other important parameter is regeneration and traceability. They are regenerable, minimize the waste, and increases cost effectiveness. Because of this advantage, we offer to use these green adsorbents in our studies. And also recently, most of the studies, when you take from the Web of Science or the other literature, you can see green chemistry and green adsorbents is the very most popular topic. Yes, we can continue. The other slide, please. Yes. I will mostly talk about adsorbents today because my studies and my topics are absorption. My study is about absorption of radionuclides or heavy metals. So this topic is very important for me in my research group, in my laboratory. We are preparing, synthesizing different green adsorbents, and we are synthesizing new material for absorption process. Because of that, today mostly I will talk about the adsorbents. Like activated carbon, these adsorbents are really very popular, and you can make a composite with different, for example, biopolymer or the other organic chemicals. You can prepare new adsorbents. These organic and inorganic adsorbents, I say, can be used, including activated carbon and other carbon-based absorbents such as biochairs, polymer materials, zeolite, biofiles, and farming waste. Also, nanotechnology has been used to resolve the no, you can continue. Because this nanostructure adsorbents have really high surface area. Because of that, your absorption process, your removal rate is high and high efficiency. You can remove the pollutants with high yield. So we offer to use these adsorbents. Yes, we can continue. Yes, environmentally friendly adsorbents, like we can produce from agricultural waste, animal waste, mineral resource, like clay or zeolite resource, industrial waste, municipal solid waste. These nanoadsorbents, like metal oxide-based nanoparticles, including oxide of iron. Iron has good selectivity, especially for metals, because its chemical reactivity is very high for heavy metals and radionuclides. Because of that, most of the researchers are used iron oxide. The other magnesium oxides, maybe zinc oxide, titanium, and like carbon nanotubes and like graphite or graphene. These are used to remove pollutants mostly, but such activities such activated carbon has many limitations, including low generation capacity, that can be toxic for many living organisms, and its use and use are relatively expensive. Therefore, to minimize the cost and produce environmentally friendly natural adsorbents with high efficiency, green adsorbents are highly effective with low cost and biodegradable. Yes. I say these bioabsorbents used for heavy metal removal ions and mostly dyes from polluted water. The dead biomass, such as bark, sawdust, heat, natural fibers, cotton or plants or flax, and the other organic substance like polysaccharides or biopolymers such as alginate, cellulose, starch, chitin. They are all used for bioabsorbent synthesis, and they are biodegradable, and they improve the absorption capacity of the some of the material. I take bioabsorbents for especially biorenovation. We can use algae, bacteria, fungi, or yeast. They have also very good removal capacity for water pollutants, removal of water pollutants. You can see the especially bacterial cell wall composition used for removal, because why they are using this material has different functional groups, and these different functional groups play a very important role for binding the pollutants. Because of this, recently people are using these materials for remove the toxic metal ions. Yes, we can continue. Yes, carbon quantum dots. Carbon quantum dots are maybe studying many years ago. They began to study, but nowadays carbon quantum dots are synthesizing from different sources, different carbon source. Especially in my studies now focus on carbon quantum dots because they are green absorbents, and they are using various categories of water contaminants, including heavy metals, radionuclides. What are we using? We are using a biosource for produce these carbon quantum dots with a simple and environment-friendly method, green method. We are obtaining very high, high selectivity and high removal capacity carbon quantum dots. They are high surface area, especially large surface, specific surface area, and they are inexpensive. You can use, for example, apple or coffee, everything you can think, which is including carbon. So most advantage is cost effective and easy preparation and high absorption capacity. Yes, we can continue. I say these materials are inexpensive and they can be synthesized from waste green source. Especially after highly cited carbon nanotubes and graphene, one such emerging green, affordable, and most easily synthetic carbon nanomaterial is carbon nanodot. It's characterized by their low toxicity, biocompatibility, and abundant edge defects, and easy surface functionation. Carbon dots have drawn the attention of not only academic researchers but also the industry domain. Their unique properties make them versatile and promising for a wide range of applications, such as optoelectronics, catalysis, biomedical imaging, drug delivery, environmental monitoring, light sensors, energy storage, chemical and biological sensing, water purification, food and agriculture. The emphasis on the synthesis of green, I said, low toxic and biocompatible, and they are a very big potential green material for reduced environmental impact and improved sustainability is a challenging task. Especially you can see from the picture, there is a simple method, hydrothermal carbonization. You can use apple peel or lemonade peel, whatever you want, you can use. This study is about carbon quantum dot synthesis from apple peel with a very simple method like hydrothermal carbonization. You can see they use this carbon quantum dots for removal of methylene blue. You can see when they react with methylene blue, the photoluminescence properties are changing. Yes, you can see methylene blue and treated water. They are clean and they also have a dual effect. Like one is removal, the other is sensing. Yes, we can continue. With carbon quantum dots use many areas like energy application, environmental remediation, imaging sensors. You can see the synthesis method top down. Especially in my studies, we are using hydrothermal synthesis. Pyrolysis is also using. You can use microwave irradiation or, for example, electrochemical oxidation you can use. I said you can obtain from the biomass, microorganisms, and synthetic polymers when you compare for the composite, you improve its capacity. Yes, we can continue. This biosource as a green precursors to carbon nanomaterials are opening up a huge opportunity to fabricate inexpensive materials of the future, which may be used as sensors, electronic devices, or adsorbents. The green precursors may be classified into biopolymeric-based waste bioresource and various microorganisms. I say with very green, you can obtain green chemistry method with low temperature, low chemicals, you can obtain these nanomaterials efficiently. Also, microorganisms are used for this material synthesis, and you can use the other nanomaterials such as zinc oxide. You can prepare a carbon quantum dot nanocomposite. These microorganisms, when you use microorganisms, the carbon quantum dot has also proven to be very advantageous in terms of low toxicity, improved quality of the carbon dot. You can use algae, yeast, bacteria as a green resource for carbon dot synthesis. I said also BRC molecules you can use glucose, aspartic acid, alanine. According to your aim, you can choose one of the source of carbon, and you can prepare this carbon quantum dot. According to your aim of your study, you can make a composite with carbon quantum dot. I will also talk about my study about carbon quantum dot. We use carbon quantum dot from mushrooms. We bought from market. We synthesize carbon quantum dot. Then we use alginate and we obtain a hydrogel, and we use them for removal and recovery of lanthanum and cerium rare elements. So they have good removal capacity, and they have dual effect, because when you put these materials under the UV light, you can see their light. When you react with, for example, uranium or lead solutions, their lighting is changing. So we can talk about its sensor properties. Yes, we can continue. Yes, natural polymers. They are key polymer materials. Also, recently, most of the natural polymers are using in synthesis of green adsorbents, green catalyzing. They are extracted from sources like microorganisms, algae, plants, and animals. They have long been used in biomedical science, from pharmaceuticals to tissue regeneration. You can see from the figure natural polymers and their structure. In contrast, synthetic biopolymers are artificially produced in labs and classified into categories like thermoplastics, thermosets, and elastinides. Some common examples include polyethylene, polystyrene, polyvinyl chloride. These polymers typically derive from petroleum-based monomers. So they are not, we can talk about the green synthesis or green chemistry when we use this material. These natural, especially natural polymers, both play a natural and synthetic, I can say, polymers both play a very significant role in wastewater treatment. Arginal, Yusan, and polyvinyl alcohol are popular choices due to their binding properties. and their functional groups, they are using for the bond to pollutants, because most of you maybe study environmentally. Functional groups are very important when you are studying absorption. Because of that, we can improve the capture radionuclide ability, enhancing water treatment efficiency with these polymers. Future research should focus on increasing the selectivity and stability of this material. Most of the researchers are now studying on this subject, because stability and selectivity is the most important parameters in our studies. Yes, we can continue. Yes, I will give one example on about our study. This published 2 years ago. This research emphasizes the use of polymer-based solvents for the effective treatment of radioactive wastewater. The aim of the study is preparing innovation isonat structures that enclose diatomic and organic extracts for targeted planktime uptake. In this study, I talk about researchers are studying on selectivity. Yes, in this study, our aim was to obtain a selective material for lanthanum. Because of that, we use organic extracts, which is good selectivity for lanthanum. Also, it published a very good journal. Yes, continue. What is the advantage and challenges of this polymer interconnection with extractant? Simple preparation process, their advantage, applicable to a wide range of selective extractants, easy separation of solution and resin. What is the challenges? Steric filtrate. Not all extract molecules are acceptable for effective extraction, and inactivation of the extractant agents can result in poor selectivity. Yes, we can continue. The other most popular adsorbents, I think, nanofibers. Electrospheric nanofibers. They are nano-sized fibers with an exceptionally large surface area to volume ratio. They significantly increases their exposure to environment compared to microfibers. This NH contact with environmental makes electro nanofibers based filters more effective for water treatment compared to micro sized fibers. This material widely applied for water treatment from diverse types of pollutants, including dyes, heavy metals, and radionuclides. They have simple production. They have flexibility and reversibility. Membranes are popular for, especially in dye removal. Among the most widely used for water treatment purpose, polyacrylonitrile, polyamides, polyvinyl chloride, cellulose acetate, polyacetic acid, polyurethane, polyethylene oxide can be named. When the metal organic frameworks are integrated with electrospin nanofiber surface, their charge and high surface area, the key factors in absorption are synergically optimized. So their removal capacity, their cleaning capacity is improved when you integrate with MOF or the other metal oxide, like zinc oxide. I am talking about this because we use zinc oxide for synthesizing of nanofibers. In our studies, we really obtain the high absorption capacity when we use nanofibers. Yes, we can continue. This nanofibers, you can continue with electrospinning process. This process is employed. You have to use polymer solutions and strong electric fields to produce nanometer-sized fibers. It's really very simple method, but after obtaining the fibers, you can see this. You produce a very large surface area material. When you obtain material with electrospinning, when you synthesize fibers, you can use these fibers in medicine, biomedical, removal of pollution, filtration, textile sector, food, or tissue engineering. It is really recently most popular subject. Yes, we can continue. We can change the slide. Yes, beginning of my presentation, I said I will talk about artificial intelligence in chemical research. The role of artificial intelligence in chemical research are really not in chemical research, actually. In many areas, artificial intelligence are used. In chemistry research, how can we use traditional methods such as X-ray crystallography or and cryo electron microscopy are time-consuming and expensive. This artificial intelligence models, particularly DeepMind AlphaFold, use deep learning to predict protein structure with remarkable accuracy. This AlphaFold has been instrumental in accelerating drug discovery by providing structural insights to receptor-related proteins, and other artificial intelligence models such as ROS, CPA4, completed AlphaFold in solving complex biological problems. Also, its use in impact on drug discovery enables faster identification of drug targets, reducing research time from years to months. It aids in the design of new pharmaceuticals by prediction how drugs interact with proteins. It contributes to advancements in personalized medicine and treatments for diseases like cancer and neurodegenerative disorders. So recently, maybe about 10 or 5 years, artificial intelligence in science are using mostly. Yes, we can continue. Artificial intelligence driven drug discovery leverages artificial intelligence to accelerate the identification and development of new pharmaceuticals, IQAC, including antibiotics, antivirals, and other therapeutic agents. This approach significantly reduces the time and cost associated with traditional drug discovery methods. In machine learning, we are using in our also. I believe you are also using machine learning in your studies for compost screening. Machine learning can be used antibiotic discovery, personal medicine, drug reporting, prediction, drug interaction, and side effects. This artificial intelligence model simulates how new drugs interact with human proteins, predicting potential side effects before clinical trials. This artificial intelligence reduces the typical, I said, year to month, the drug discovery timeline, and it can be used more effective treatments, especially identifying the better drug target match. Researchers are now using mostly artificial intelligence to optimize their studies results. Yes, we can continue. We can change. Yes, advanced materials and nanotechnology. This invisibility cloak materials refer to advanced materials that can manipulate light or other electromagnetic waves to render objects less visible or completely undetectable. These materials are based on cutting-edge development in nanotechnology, optics, and material science. How they are work? Molecular toning, metamaterials, liquid crystal technologies. We can camouflage work with this technology. What is the applications of invisibility cloak materials? In military and defense, camouflage suits and stealth technology to evade detection. Medical imaging, make instruments or device transferred for better diagnostics. Aerospace, in aerospace and automotive, these materials reduce visibility of vehicles using adaptive materials. Yes, cloak materials are recently really very popular. Yes, we can continue. The other material is boron radicals. They are a class of reactive chemical spaces containing a boron-centered unpaired electron. These radicals have gained significant attention in material science and scientific chemistry due to their unique electronic properties and potential applications. They have high reactivity. They have tunable electronic structure. They have stability. Where can we use these materials? We use them in materials and nanotechnology for example, organic development of semiconductor materials for organic light emitting dyes. and organic solar cells, we can use boryl radicals. For catalyze and boron doped polyacrylic aromatic hydrocarbon synthesis, for synthesis of this material, we can use boryl radicals. Yes. We can continue. The other subject is physics chemistry. Innovation in catalysis and chemical reactions, we can talk about physics chemistry. This is efficient modular reaction in drug and material science development. This physics chemistry refers to a class of highly efficient, selective, and modular chemical reactions destroying molecular components quickly and readily. These reactions are inspired by natural processes and are widely used in pharmaceuticals, material science, and biotechnology. What is the key features of this subject, physics chemistry? High yield and selectivity, bioorthogonality, fast and efficient. When you use physics chemistry, reactions proceed rapidly. You can reduce the time and resource consumption is realized. Yes, we can continue. What is the application of the physics chemistry? In drug and material science development, we can use physics chemistry, I said, pharmaceutical and drug discovery. You can use to create a targeted therapies, including antibody drug conjugates for cancer treatment, facilities the development of new antibiotic and antivirals. I said in material science, advanced polymers, hydrogels, and nanomaterials, you can synthesize with physics chemistry. Biomedical imaging, this technique allows the tagging of biomolecules in leaf cells to study disease progression, and it can be used in PET imaging and targeted drug delivery systems. The 2022 Nobel Prize in Chemistry was awarded to Barry Shapley, Caroline Bertozzi, and Morton Mendel for pioneering physics chemistry and bioorthogonal chemistry. So this topic is new, and I think researchers should focus on this subject here because it has very many advantages. And the other topic is nanoenzymes. They are nanomaterials. They exhibit enzyme-like catalytic properties. They have advantage. What is their advantage? They have high stability, lower cost, and enable activity. These materials catalyze reactions similar to peroxidized, oxidized, or peroxide dimethyls. So we can talk about green chemistry in this section. I said they have high stability, cost-effective, and multi-functionality. Their catalytic properties can be tailored for specific applications. So this is the new topic. Yes, we can continue. Where can we use these nanoenzymes? In biomedical applications, industrial applications, we can use these nanoenzymes. In my area, especially environmental validation, we can use these nanoenzymes. For food health, food safety, also nanoenzymes are using. They help detect and eliminate the harmful contaminants in food products. In chemical manufacturing, they enhance efficiency in oxidation and reduction reactions. Recent advancements in nanotechnology have improved nanoenzyme performance, expanding their potential across multiple files. I said this is the important and very new topic. Yes, we can continue. Yes, finally, I can say that recent advance in chemical science has led to groundbreaking developments in sustainable chemistry. Artificial intelligence driving drug discovery, advanced materials, and computational chemistry is important. These innovations have profound implications for medicine, environmental protection, and industrial applications, improving efficiency, sustainability, and performance. Future research should focus on scaling up green technologies, integrating artificial intelligence more efficiently in chemical research, and developing novel materials with enhanced properties, addressing challenges such as cost, stability, and regulatory hurdles will be crucial for widespread adoption. Yes. Thank you for your attention. This is pictures from my country, my city.
Thank you so much, madam.
You're welcome.
Madam, please continue, madam, please.
Thank you so much, ma'am, for your beautiful insights, sharing your knowledge and your expertise and deliberation for our participants. And now I would like to request Dr. Milan Hadsar and Dr. Abhishek Sharma to please continue for the question answer session. Thank you so much, ma'am.
Yes, ma'am. Thank you. Thank you, ma'am.
Thank you, ma'am. Thank you for sharing your insights, ma'am. So, how's the climate there at Turkey? It's evening.
Thank you.
Okay.
Ma'am, session is open for question hours. Please mention your question in chat box.
Participants, please post a question in the YouTube chat box and Zoom chat box. Sabriya ma'am, 5 minutes question answer session is there with you.
Hello.
The participants are interested.
Hello.
All the participants are requested to please post a question in the chat box.
Hello, madam. Madam, one of the scholar asking about polymer nanocomposites.
Sabriya ma'am, are you there?
Yusan ma'am?
Yes.
Yes, ma'am. One question answer session is there. Question is arising for our participants, ma'am.
Yes, you can ask.
Yes, ma'am. Yes,
ma'am. Ma'am, question is polymer nanocomposite. Swelling, what is the swelling in nanocomposite material, ma'am? Swelling.
Nanocomposite material.
Yes, material. Yes.
Sorry, I couldn't understand.
Abhishek,
What are they or which methods I'm using?
Abhishek, repeat the question, beta.
Polymer nanocomposite material in case of swelling studies, ma'am. Swelling studies.
Yes. Regarding swelling studies, ma'am?
Yeah, regarding swelling studies for nanocomposite material, and we are using nanomaterial for the preparation of same.
Yes, we are using. Yes. For example, we are using starch or another polymers for preparing nanocomposites. Arginate also we are using, and we are also testing their swelling. We are because they are hydrogel, most of them. When if you want to use chitosan or the other, when you synthesize nanobiopolymers, yes, you have to study you have to see their swelling properties. When you want to composite, I say if you use polymer from natural source, and the other material can be from inorganic, graphene oxide, carbon quantum dots, zinc oxide, iron oxide, or natural minerals like clay, diatomic, zeolite. You can prepare for your studies.
Thank you, ma'am. Thank you so much, ma'am.
You're welcome.
Any more questions from participants in the chat box? Milan sir, any questions in YouTube chat box?
Madam?
No, ma'am.
No question, madam, in chat box.
No question in chat box, ma'am.
Dr. Sar sir is there with us, sir.
Thank you, Professor Sabriya,
You're welcome.
for informative lecture and information to this university that is 150 kilometers far from our place.
Yes, sir. It's situated in rural and tribal region, ma'am.
Tribal region. If you visit India next time, then we will go for CV Raman University.
Definitely, definitely. Sure.
I hope.
We are eager to welcome her, ma'am.
I hope.
Their
Yes,
university is
yes.
naturally very good.
Thank you.
Naturally and academically also they are very strong. They have NAC A grade accreditation from Government of India.
We would love to collaborate with you and your university, ma'am.
We have collaboration with Professor also. Yes, I believe next studies we will have a collaboration. Now I'm focused on I say carbon quantum dots. It's really very interesting topic because synthesis is very simple and you use this for synthesis you are not using any chemical. You are synthesizing with hydrothermal synthesis. For example, we are synthesizing from mushroom. We are putting mushroom, we are cutting it, and then we are putting water. Then in hydrothermal reactor, we are synthesizing. It's really simple and effective. Maybe we can continue with our studies with different source. In India, maybe different carbon source. Yeah, maybe.
She told about mushroom making carbon dots.
Yeah.
Okay, thank you,
You're
Professor.
welcome. Thank you.
Thank you so
One
much.
more question in chat box, ma'am. YouTube chat box.
One more question is there in the chat box.
Asking for some more light on biomedical application, madam. Biomedical application.
Ma'am, repeat the question.
Ma'am, they are asking for, you have already talked about biomedical application. So,
Yes, biomedical
some more
application.
about that.
Yes, biomedical application, you can use many different techniques. In my institute, one of my group are studying on biomedical application. I'm focused on environment, but they are studying on biomedical application. They are using pharmaceuticals and they are using, I said, carbon quantum dots in their biomedical imaging. They label it, they synthesis label it by pharmaceuticals for their studies. Yes, in biomedical areas, most of the materials are using, which I talk about, nanoenzymes and the others also.
Okay, ma'am.
And graphene oxides. Also, they are using in biomedical application graphene oxides because its reactivity is also very high. Yeah.
Okay. Okay.
Okay, thank you so much, ma'am, for giving your precious time and sharing your beautiful and wonderful insights with us and for this beautiful deliberation. Thank you so much, ma'am. And thank you for giving your concern for this e-seminar. And further, we would like to collaborate with you and your university also. Thank you so much, ma'am.
Welcome.
Thank you,
Thanks
madam.
a lot from Department of Chemistry and all the Dr. C.V. Raman University, ma'am.
Thank you, ma'am. Thank you so much. Now, before we proceed, am I audible?
Yes, ma'am. Yes, ma'am.
Okay, before we proceed for our second session by our respected Jhuma Ganguly ma'am, I would like to welcome all the participants once again because during the first session, many of the participants were unable to join the time initially. So once again, a very hearty and warm welcome to all the participants in this e-seminar, or that is we call International E-Seminar of IUPAC, Global Women Breakfast 2025. So where we are celebrating women in sciences and catalyzing equity and inclusivity in chemical sciences, as well as accelerating the diversity in sciences. So further, I congratulate once again the Department of Chemistry for taking this initiative to contributing to the our sustainable development goals of goal number 5 and goal number 10. So now, before I proceed, I would like to welcome Dr. Jhuma Ganguly ma'am. She is with us here in this session, in the second session. Madam, I would like to go with your brief biodata, and we would love to share that she is the Associate Professor and former Head of the Department of Chemistry in the Indian Institute of Engineering Sciences and Technology, Shibpur, which is IIEST Bhopal, Shibpur, sorry, Howrah, West Bengal. And she is also the PhD from Indian Institute of Chemical Biology of CSIR, that is IICB CSIR Lab, and degree awarded by Kadavpur University during the year 2003. And she has completed her postdoctoral tenure on Complex Carbohydrate Research Center, that is University of Georgia, Athens, from GA, USA, during 2009 to 2011. And she's right now having her current research interest in synthesis or organic synthesis, functionalized sugar-based synthesis, colloid, hydrogel, organogel, and spectral analysis, absorption and fluorescence, interaction of supramolecular assembly of synthesized materials, glycobiology from natural resources, algae, mushrooms, bacteria, etc., and microencapsulation of nanoparticles and applications. She is also felicitated with various awards and honors and memberships. She is the fellow of the Indian Chemical Society, FICS, also a member of Association of Carbohydrate Chemists and Technologies India, and also a member of Indian Photobiology Society and member of CRSI and Young Faculty Research Award she has received in 2015. As well as she has a number of invited talks, and she is also invited for Indo-FOE Fellow 2018 in Potsdam in May 2018, which was organized by Alexander von Humboldt Foundation, Germany, which is a scheme of DST and IIT Kanpur, India. And she has also been delivered a lecture of Professor Asima Chatterjee Memorial Lecture 2024 at Dr. C.V. Raman University, Bilaspur, Chhattisgarh also. And she is a recipient of the Memorial Award 2024 from Association of Carbohydrate Chemists and Technologies, India, as well as Lucid Colloids Limited, Private Limited. She has supervised a number of UG, PG, and PhD scholars also, 90 PhD produced, 11 UG, PG, and she has supervised 45 UG, PG students and other scholars. So this was the brief from of our respected next speaker, Professor Jhuma Ganguly ma'am. So I would like to welcome her in this session of this international e-seminar, IUPAC Global Women Breakfast. Welcome, ma'am. Welcome to the e-seminar of Dr. C.V. Raman University.
Thank you, Madam, for your nice introductions for me. And thank you, Dr. Rashmi Bharma, Dr. Milan Maiti. We already was in last year in this university too in physical mode. And this is my online mode, but I'm missing the place. And I can actually, few places are very familiar with my visit. That's
a lot of memories.
Recognize from Milan is sitting in the room, etc. So it's like I'm very familiar with your university too.
Thank you, madam. Thank you.
So today's talk is, I already mentioned, madam already mentioned about the research area, and actually I focused usually on the synthesis part and their associated some phenomena and trying to develop some using this developed material for the application based few works. All are not successful at per level, but I tried, the students are, my scholars are tried to reach something to outcome should be there from our synthetic material. So now I am sharing my slides. Is it visible?
Yes, madam.
Yes, ma'am, it's visible. You can proceed, ma'am.
Okay. So now I will proceed to my lecture, and I'm showing one picture where this black bone, actually black dotted, this one is the sugar moieties, sugar backbone, which we are very familiar surrounding us, and that there is some colorful symbols are there, geometrical figures are there. These are actually related to my topic, that is aromatic anchored sugar hydrogen. So these are like variety of aromatic moieties. If it's grafted with the backbone by chemically, so covalent bonding will be there. So there will be some very interesting phenomena will come if the moiety will change. So that is the actually today we will only sharing this thing. And here first one, suppose we have cellulose. So cellulose, what is the main functional group? That is there is, I mentioned that two type of one is the primary hydroxyl group, this one, and another one is the secondary hydroxyl group. But what is the difficulty to use the cellulose for the development of the sugar-based material? Its solubility. It's not soluble in common organic solvent. We need to attention. First, we need to attention for solubilize the derivatized of the cellulose. So we can go further for the functionalization. That is some difficulties, but scientists are already worked so much things. I little did also, but that is some difficulty. So we next one. I use chitosan. Chitosan is very easy to prepare the functionalized moiety, and that is because of its presence of NH2 group, amine group, and we quickly use this one for the better result. And again, we will use nowadays we using the material pullulan, that is actually starch degraded trisaccharide moiety, and it is soluble in water. So we focus this one as it is degraded product of the starch moiety. Next one, and there is an interesting backbone actually. One is the 1,4 linked and another was the 1,6 linked, and that is a good thing to be used as a biological purposes or evaluation and interactive purposes. We can use this pullulan. Next one is the gelan. Gelan, actually the anionic polysaccharide is actually unit is the tetrasaccharide, and it has reached in the functional group of primary hydroxyl group, secondary hydroxyl group, and one acid group. Other than it has one rhamnose moiety. Rhamnose is very interesting because it is a deoxy monomer. And this tetrasaccharide unit is very versatile of the functional group. And another part, gelan is also we found in our surroundings as a food product in a gel material. So obviously gelan has no cytotoxicity. So if we start any productions of material development with the gelan, it is a very easy, cheap source and no toxic effect. So that is one approach. And another part, gelan is very thermosensitive to produce the hydrogel. Whatever the functionalization you make, if you unreacted keep the unreacted for the carboxylic acid group and you heating the molecule, the moieties or the derivatives, you will get the hydrogel. So you don't need to put the any cross-linker further for the formation of the gelan. So that is some beauty of the gelan I observe. Next, so we will today coming not in the gelan so much or pululan, but I am just going first with our theme of our research also. So we synthetic strategy. So here is we are dealing with the different type of polysaccharides. So synthetic strategy, we have to develop some strategy for each cases. Maybe one is the soluble, one is not in the soluble in water or organic solvent, or how to isolate, how to purify the material after the reaction is over. That strategy actually we are developing day to day in derivatization preparation. Second part, if this hydrogel or this some amphiphilics or this type of moiety, colloidal moieties will form, the structural elucidation is a challenge too, because the NMR not only serve to characterize the material because it's a gel material. So we need to recheck and check and investigate deeply how we'll conclude our substitutions or the chemical reactions were successful. So that is some challenging. So structural elucidation part is very much always we put emphasis for our research to successful productions of the development of the material, sugar-based material. Other than this one, another part I already mentioned, the synthesis, structural determination, and we screening the efficiency of the material, how will be applied in our system, in the current industry or in biomedical application. And for this one, I have make my research tree little bit. So like there is a wastewater treatment, and for wastewater treatment we are going to adsorb or sensing with the metal, heavy metal or metal cation, anion, then organic pollutant like gas or any other chemicals, then toxic dye, obviously that is another part. After that, wastewater during this actually work, I also sensing taking the identification of the some cation anion using this hydrogel type of material. We already used our successful showing their activity as photocatalyst and the sugar gel catalyst. We can use these two terms for the application. Other than in the gel, there is a very interesting features will come sometime, that is the hydrogen bonding along with the chromophoric self-assembledness. This will make some interesting features, and sometimes from the disaccharide if we prepare or the monosaccharide, we can get the low molecular weight gel too. So that is something, the interesting feature will come and study accordingly. And biology part, we studied the drug delivery definitely, because sugar is the best, sugar hydrogel is mimicking the cell matrix. So drug delivery in vitro or in vivo is very interesting and give a very nice results. Then protein binding of the protein, how this drug delivery will occur. First we testing by the protein binding, then antimicrobial and including means antibacterial and antifungal, both we found from this functionalization process, the application part. And antiviral, we already, for antiviral it is not directly from only the organic moieties are responsible. We are using some nanocomposite. And obviously, if the hydrogel is the same fluorescent, we will definitely it's able to mixing with the system or and we'll get a nice picture of the cell. So it is a cell imaging purposes we can use. So we have a few important paper related to, I just already, there is some list. Now, what is our strategy? What is our strategy? First, is it visible?
It is visible, ma'am, but no, it is audible also.
Okay.
Okay.
So now this one is the first the slide. So how we functionalize. So that is our we are thinking according to the functional group. So there is a OH. So that maybe from the first we will go for the base treatment, so that base is abstract the proton and we can bound some alkyl group or some this type of moieties. Second one is for the tosylations. Third one is the epichlorohydrin type, epoxide type of, or chloroacetic acid. This is some few things we have studied, but all are successful not for particular for a specific chitosan. Maybe it may be successful for the pullulan, not the chitosan. So that there will be some variation. We'll try a little bit and then go to the NH2. NH2 is very specific. We have best one is the seed-based preparation. It is very easy, and even for during the seed-based preparation, we so that is subsequently it will give the gel immediately. But amide formation sometimes not give the gel immediately. You have to make some processing. Then anhydride reagent, you can treat it with the anhydride, then acidic for cationic type of some changes. And you can, if you want to go for the fluorophore, directly you can fluorophore by some this type of moiety, or bromine type of naphthaldehyde moiety you can input for the NH2 group. And after that, we can go for the carboxylic acid group functionalization. This will done by amide, by thiol, by ester, and some different approach maybe is not so easy for the ester formation or amide formation. You have to think on the for long chain or some special purposes according to we can make by, or we can incorporate by long chain or fatty acid for make a nice gel. So this is some approach. We always have some summarize this one, and scholars are trying whatever they feel. Sometimes they are successful in one shot, but sometimes they need maybe some more time of trial to which one is the best for the for a particular polysaccharide, according to their solubility in the organic solvent or in the other thing. So now the structural here today I am focused only the, and this is I am personally very much feeling interest to see how it works, or hydrogel how it forms, or what is the role of the aromatic moiety to show is some structural features and their hydrogel network structure. So this one during this thing I actually found some interesting features, structural features, and that I want to share for this lecture. And this is two things actually for this one I only focus on the ESIPT, that is the proton excited state proton transfer, and that gives a very prominent prominent fluorescent for a hydrogel formation. So there is a three. I will just go through one by one. First one, I will prepare. Here is the ESIPT involved between the one naphthol moiety is there, naphthalene moiety, and the and the imine bond. So how will prepare? How I prepared this one? This one is the just chitosan moiety. I just showing one monomeric unit only, and here is the beta naphthal one monoaldehyde, one aldehyde aldehyde, and this one just making with the SIP base formation. There is a chance, there is the criteria for the ESIPT based fluorescent fluorophore or fluorescence ability, that is the proton transfer we got, and this one is gives a very nice gels, and this one. So during this thing, that is we have to first prove that one, that is the moiety, the aromatic moiety not absorbed in the chitosan backbone, that is not. So that's why after the gel formation, because it is very quickly the gel is formed, we wash thoroughly by alcohol or etc., sometimes in other solvent too, so that the gel will not dehydrate it but make the gel. It's like some, we need some trick sometimes to remove the this organic molecule, so that after that we will go for the NMR and for sometimes or IR. IR after the aerogel formations, that is the dry with the dry gel powder, and NMR with a particular solvent if it's suspension. But sometimes, most of the cases, we are very unsuccessful to make a clear spectra with this hydrogel. So this gel is prepared. Now, what is this? This is fluorescent gel. So we'll checking if the fluorescence often will be enhanced or quenching, will give some application based work. And we found actually that cadmium is very nicely fitted, particularly, specifically or selectively this gel porosity, but not the other metals. And that is, we actually, after that it will be a great good job to identify why cadmium is this one. And again we found another thing, reversibility, so that if we put the EDTA, that cadmium is actually abstracted by the EDTA or chelate with the EDTA, and we will get the gel back with this fluorescence. And this thing means actually predict that this cadmium is actually loosely bound or labilely form a labile complexation with the gel moieties, and then EDT is a strong chelating agent, so it can capture, but in between no other element can be captured in this interalia of the hydrogen. That is interesting, and we repeatedly reversibility, doing the reversibility test, we found the porous gel too, and this porous size actually fitted with this one cadmium. That's we actually monitor, and that does, but particular size actually will giving this selectivity for the cadmium for withhold with the gel, not the other metal. So this one is taking first initial work. After that, we have synthesized another material, some imidazole based, but the fluorescence is caused by the ESIPT. So first we prepared this thing, bench imidazole type of moiety, and we attached with the implanted with the chitosan backbone through his NH2 group, and we got a very nice self-assembled rod-like morphology under FESM image. We found this one, and again I just interestingly just put the different type of metal because we previously got the cadmium. So see what will happen here. But here cadmium marker, no cadmium is actually, or cadmium or any metal is scavenged, but only the mercury is actually scavenged, but the mechanism is little different. The mercury is scavenged, then if you put their Na2S, the mercury is again coming out from the system, and this mercury will be not back in the solution. But if you add the mercury again in the water phase, you again it trap in the gel, and if you put the Na2S, again it will be dropped down. We just collect this HGS from the Na2S. After the, this will collect the precipitate, and we found not only some combination of the Na, HGS and Cl2, this type of material will come by precipitations. And so this one is a very nice for the directly, and this is something that you can directly use this insoluble hydrogel for the soluble detection of the soluble mercury directly, and it will there is no byproduct or etc. So you can use the gel repeatedly, so reversibility. So it is the same material for detection of mercury in water system. Next part we synthesized, actually we use some resorcinol modified by formulations and attached to this one. But here we intentionally keep one aldehyde group in a such a, now we have some control how to control. We adding the gel formation, but don't add a so cross-linked gel. So we make some aldehyde group unreacted in the system. Few, and but still gel is there because the different type of the hydrogen bonding cross-linking, and here also some ESIPT is there. Now what will happen, this molecule looks like under UV some yellow and bluish in the fluorescence light. But if we put hydrogen in this particular hydrogel, it will just enhanced the hydrogen actually enhanced, or just like a inducer for the fluorescent increased in enhancement for this particular hydrogen. Now, but no other analyte, like we can actually we use the hydroxylamine, that is NH2OH, and then NH2 only the aniline, pyridine, etc. But it's not happen. Only the hydrogen gives this so jump of the fluorescence. Now, what will happen? We will go for the NMR studies, NMR titrations, or etc. But it's very difficult. Because it's the gel, but we run like for proton NMR, we run like 48 hours, and we'll get to identify a little bit initial the aldehyde presence and absence, that much, but not the what will happen the system. Any peak, new peak will appear, that is not be characterized by the NMR. Only the presence of the aldehyde and absence of the aldehyde we identify. And that's from this one we conclude that maybe hydrogen makes the double seed base and makes a long conjugations, and that actually increase the fluorescence of the whole moiety, because there is a double ESIPT moiety, the area also some possibility also there. And in this case we use so I will show this is our hydrogel, and this is the after the addition of the hydrogen there is a double seed base formations, and actually there is this unit have 1 2 3 4 seed base is there. And again the same image, actually this FSM image show that average particle size from initially it is 149, but the hydrogen after the addition of the hydrogen we got 295, just double. And you can see the morphology of the peaks, morphology of the material change, you can see that is sum the size accordingly. And then we put whether it is the seed base or not, that we have to put very easy way, just put some HCl. Only this part, actually from this part, this labile hydrogen part is easily clipped or partially clipped, and the fluorescence arised is just quenching by addition of HCl, so that there is some labileness of seed base is produced, that we make some conclusion. So I'm not going, this resorcinol also have some cell imaging. I'm not focusing on these things, only to go to for the next slide, next compounds, where we use this aggregation. We are checking what is the aggregations of found in this hydrogel if we use the anthracene moiety. So next one is the anthracene related. So we prepared 2 anthracene. Again it's going. So there is a anthracene, two type of derivatives we prepared. One have anthracene and there is a one CH2 and one pH. Another one, there is a one oxygen, then CH2. So we make this one is flexible, this one is also flexible. But see what will happen. So anthracene have own fluorescent. We don't need the other fluorescence phenomena like SIPT. And anthracene has the phenomena for the aggregations or pipi stacking phenomena too. So see what will happen. This aggregation will be, we can get captured in the hydrogel form or not. That is our motivation, and we get a nice capture. So first there is some morphology. So this one is a not flexible. We'll get some rod like, and here is not some amorphous type of material, and this one is so now this is the some fluorescence spectra for two molecule. First one is the from the, there is no only the CH2 1 pH, another one is the OCH2 pH. So for first one, where is the CHA pH? This type of moiety in presence of water is 0 first, and then slowly we increase the value up to 90%. Then during this time, we observe that there is an extra peak will arise in the region of the red towards the higher wavelength, and this will not happen for the OCH2 pH, benzyl type of moiety. So we just after that we'll going for the pH variation. So peaks will be more visible with the increased the pH, but not any this new peak will not be shown in the CHABN. So after the temperature variations, spectroscopy done, fluorescence spectroscopy, and we see with the increase of the temperature, the fluorescence will drop. This peak will slowly intensity drop. So fluorescence is not concentrated dependent. This is some concentrated independent phenomena. So definitely the moiety have been changed, and from this concept, from these observations, we make a conclusion that we have some aggregation, but this gives some excited state peak. And that's why I describe this one as exciplex. What type of, it is very difficult to predict within the hydrogel because we have no crystal type of structure, but we predict that anthracene moiety may be collapsed to each other and make some excitation, but there still these anthracene moieties original peak will be lower and new peak will arise, and this conformation we predict as exciplex in the formation of hydrogel. That is only possible in hydrogel in presence of water if you increase. So the non-aromatic moieties are close to each other and give this excitation. But for which one is the flexible OCH2, because of this O oxygen, this is flexible, and this one is interfering with the hydrogen bonding with the solvent, and so it's not inhibit the formation of the this type of exciplex formations, and that's why we'll not getting this phenomena. So this one is actually nice, unique. This one is actually by the hydrogel formation. We capture this thing as a exciplex formation in from the anthracene moiety, and we can control the formation or exciplex. We can formation by their rigid structure or flexible structure. This part, and obviously we are perform some extra few applications with cell related, but I am not considering here for the lecture, only showing the fluorescence part. After that we are making another ESIPT based molecule, and also there is some aggregations too, and but this moiety is biologically active. This is a quinazolidine known moiety, and this one have showing some interesting phenomena other than only for antral naphthol moiety or benzimidazole moiety than the anthracene moiety. See what will happen with this moiety. So this one we prepared actually this quinazoline new moiety with a new synthetic procedure is the nano copper nanomaterials, and we actually first how we distributed the quinazoline moiety. First time we make the hydrogel for the CLSM, and we observed when with respect to only chitosan, there is the blank one. After the formation of the quinazoline or implanted the quinazoline moiety in the hydrogel backbone, then we will get a scattered this type of some image, and we will make a consistency or a curve of their fluorescent efficiency also. And then we'll go for how it looks. It looks in different category. Different category means if you have wet gel, this is dry gel, and this is some gel in the tetrahydrofuran. This is in normal light, and this is some fluorescence light. We'll see the color will be changed because aggregation will be changed. Their the emission property will change depending on the assembled nature. Then we'll going for the temperature dependent. Obviously, the fluorescence, the aggregations will be lowered. If we go for the temperature will rise, but the pH, what will happen? There will be in higher pH, we'll see the little red shift of the blue shift of the peak. Because then in higher pH, actually quinazoline moiety have some proton, and that is some ionic concentration of the this moiety will increase, and it will some higher energy, and we will see the blue shift. So again, after that, again we will go for temperature dependent. There is some unique feature. So when the gel is there, colloidal, and after some time it will go to gel to the sol. And here is a jump of this one. First, initially the concentration with the temperature, the fluorescence will decrease because of the aggregations are dropping, but still the colloiding nature will be there. But at a certain temperature, it will be the critical temperature for gel to sol phase, and we will capture here is some certain jump again to increase the solution phase. After that, it will again in gradual way slow decreasing their fluorescent intensity. So this one was done after the, so it is like a phase during the phase, maybe phase change we captured, the fluorescent will increase, gel to sol, some rotation or some stagnancy will be there, and that's why it will happen. And accordingly, we will go for the some DLS characterization, how the particle size will change with the solvent in water, and in the TH is the aggregating solvent. So the particle size will increase with respect to water. That we also conclude with this quinazoline based gel. And for their fluorescence stability, how much? For with respect to water and the THAB, I already mentioned THAB is aggregating, and that's why their average lifetime we a little bit increased, and that is 2.25 nanosecond we captured with respect to water in 90% water, and it is 2.02. So stability will be different for organic solvent to water, and aggregation will be hampered in presence of water. That's are okay, because that time only the quinazoline moiety will be much more be in a water bounded with the cross-linking with the water hydrogen of the water molecule. After that, we're doing some theoretical part, this one by correlation, and we found some non-bonding interactions are playing in there with respect to other than the hydrogen bonding or pi stacking or etc. This RDG analysis can predict the different type of associated interactions for the in the hydrogen that we are trying to develop, because sugar is a long molecule, but we are taking some model part and cutting from this moiety and checking whether these are consistent with our this fluorescence phenomena or this quenching phenomena or not. That is some supportive experiment we did. After that, definitely this cell imaging is interesting because we are doing the cell imaging in presence of water and in presence of THF, because we are they show their different type of phenomena in both the cases. In water, actually, in what only the hydrogen suspended in 90% water, we going for the cell imaging, we see only the nucleus of the cell. But if we change the mixture of water and THF, we found not only the nucleus, we also found the some cytoplasm. So cytoplasm inside the nucleus that we found. But in only water, we only found the nucleus, not the cytoplasm part. So cell shape will not be actually found in the presence of water, but THF is can give an idea what's the looks like. So that is something difference we found in this special features for cell imaging during our cell imaging study. And after that we'll going for actually drug delivery with this one, and we make the curcumin as is not so much soluble in water, so try to see if the hydrogel is a good scaffold or encapsulating agent for the delivery of the curcumin. So we make some drug carrier for this hydrogel in a milligram region, then curcumin concentration, and we see the curcumin is 3 microgram per ml, we can encapsulate 80% of the drug in the hydrogen. So that is some observation is really nice. And now how to release this one? We actually whatever the normal normal pH we capture, and we tested this release with the pH 5 and pH 7.45 7.4, and we found 7.4 will be the best for the release of the curcumin from the hydrogen. So curcumin is is like we can use actually the cargo, we make a cargo with this hydrogel for the delivery of the curcumin, or we can use this one as the drug delivery system. So that's we can do. So I think I can finish because it's half an hour. I will not make much more slides. Okay. So at the end, I will again acknowledge the funding from the different sources. Without this funding, the whole our research lab, my research team will not be formed, and institutional support for the instrumental facility is another part. Without this instrumental facility, we are unable to perform our AMR. That is another part. And another the collaborators for the biological, sometimes we are going for some industrial purposes, sometimes we are going for coating or etc. We have counterpart, we have lots of collaborations for this part. And the hydrogel groups without the scholars is not possible. So that's why I have few their efforts actually I started my hydrogel work from 2014, and so 2014-15 around, so around 10 years I'm started working with the sugar based hydrogel. So now we can have some, the students are now very happy with this theme thought. The sugar hydrogel can make some changes in the current scenario, or they can demand some applications, etc. So up to this one, I can conclude my lecture here.
Thank you, ma'am. Thank you so much for your interactive talk. Thank you so much, ma'am. Now it's time for question ask. Please mention your question in chat box in Zoom or YouTube also.
You can drop your question in chat box also. Ma'am, very nice lecture, ma'am. Very nice.
Thank you.
Thank you. Thank you so much, ma'am. Is there any question from scholar and students? You can raise your hands also.
Just can I stop my sharing? Otherwise, I can.
Yes, madam.
Go for it.
Yes,
So I
ma'am.
stop
You
my
can stop.
first. Yeah. Okay. Now, if you have any queries, students, so you have lots of sugar surrounding from morning tea to night cold milk too.
Yes, ma'am. Definitely. Abhishek sir, any question is there?
No, madam. Someone is typing in chat box in Zoom.
You can unmute yourself and ask question directly also.
So hydrogel from toothpaste also you just use the hydrogel.
Yes, ma'am.
And we put some fluorides or etc. So hydrogel is like a super absorber. So absorb but not react. Whatever you can put it, you can useful things is a limit, and you can make a reflection of application in a particular product. Even the hydrogel, if you spray, make a emulsion and a spray in your car or etc. during your fog or some mist, so it actually absorb the water, and your glass screen of the on car will be like a clean. So that is also something you can make some startup or etc. using the simple hydrogel, making from even aloe vera. You can make it as a product.
One question is there, ma'am.
Yeah, hydrogel are water absorbent cross-linked polymer
Add
networks that
water.
hold large amount of water. Yes, hydrogel actually it's the water used as a cross-linker here, even, and but it insoluble. The volume is so much it insoluble in water, but it again if you put some little bit water will be absorbed too. And most like ice is a cross-linked of water, and it to float on the water. So hydrogel is not like gel form, not in a solid form.
Okay, ma'am. Thank you, ma'am. Thank you.
Okay, thank you.
Any other question?
So gel is not there. We are always like gas, liquid, and solid phase. We are not so much aware of the gel phase. So students have not so much queries maybe.
Thank
I
you.
think no more question, ma'am.
No,
Okay.
madam.
No, ma'am. No
Thank you. Thank
question.
you.
If,
The
if
each
anyone
member
have
of
question, can
the organizing committee. Huh? Hello.
yes, madam.
Yes, ma'am.
Hmm.
Uh,
Hello.
one question there
Milan,
in the
Dr.
chat
Milan
box.
says something.
Yes, one question there in the chat box.
One question I have already mentioned. Any other question? This I already mentioned.
Okay, okay, madam. Okay.
Hmm. Okay, so then
No more.
thank you, Dr. Milanai, then Rashmi, and then Madam also, that you are giving me this opportunity to show the some hydrogel works from my laboratories, and is very nice to meet you in this platform also.
Thank you so much,
you.
ma'am, for your wonderful insights and sharing your knowledge with us. And more, we need to know, we need to learn our student fraternity, our all academic fraternity, and more eager to learn more. So we'll be there with you in some other conferences, seminars, workshops, and lectures, definitely. And thank you for your wonderful deliberation, ma'am.
Thank you, ma'am.
Thank you so
Thank
much.
you so much,
Thank you
ma'am.
for
Thank you so
providing
much.
precious time. Over to Dr. Rashmi ma'am for further next session. To continue the session
Okay.
further.
Okay. Ma'am, the next session is session 3 of Dr. Rachna from Nepal,
Dr.
Tribhuvan
Rakesh.
University. Dr. Rakesh Yadav. Rachna madam, are you there?
Ma'am, I'm here. I'm audible?
Yes, madam.
Yes, ma'am.
Dr. Rakesh,
Good
please
afternoon.
continue the session, sir.
Good afternoon, ma'am. Good afternoon, everyone.
Good afternoon, ma'am. Welcome, ma'am.
Thank
Welcome,
you.
ma'am.
University.
Thank
Welcome,
you.
madam.
Thank you.
How are you?
Should I start?
How's the climate there, ma'am?
Today it is cloudy.
Cloudy.
Only day. Yeah.
Okay, that's fine.
What temperature there, madam?
Yeah.
What temperature there?
Temperature is 11 today.
Oh my God.
Okay.
In my area, it's 11.
But
In the
it's
morning, it was little less.
not the same in Chhattisgarh. Okay, you can continue the session, sir.
Okay.
For proceeding further,
Okay, I'm starting with my session. I'm sharing my screen.
Just a minute, ma'am. Let us just have your brief biodata, your brief profile. So Dr. Rakesh Yadav sir will just share your brief profile, and thereafter you can continue, ma'am.
Okay.
So let our participants know, and let's move on with a chemical handshake once again.
Rakesh sir is not audible, ma'am.
Rakesh Yadav sir, you're not audible. No need to just delay the time. You can continue, ma'am, or Milan sir, you can also continue. Any one of you?
I can't.
Okay.
Very good afternoon, Dr. Rachna Ghimire ma'am. Ma'am, she is a permanent faculty of Department of Physics, Tribhuvan University. She worked as coordinator of the Department of Physics, Trichandra College, Tribhuvan University. She is treasurer of Nepal Physical Societies, and she is working to uplift women's education as an executive member of various social organizations in Nepal. Being an immediate past executive member of the Nepali Society for Women in Physics, she got an opportunity to encourage young generation in science. Academically, she has been teaching for the last 20 years. Her research field is kinetic Monte Carlo simulation for growth of thin film SOS model by using Bickel algorithm. Recently, her research has focused on solving problems in Nepal like earthquake prediction, lightning, so on her students. Thank you, ma'am, and welcome for the session.
Welcome, ma'am, to this IUPAC Global Women Breakfast. So let's have a breakfast.
Thank you, sir. Thank you, sir, for your brief biodata of madam. Madam, can we continue?
Yeah. Allow me to share my screen.
Okay, ma'am. Okay. Okay.
Abhishek sir, you are sharing or madam is sharing?
Madam is sharing, madam.
Okay, okay.
I'm sharing, but here it's coming host disabled participant share screen.
Okay, Abhishek sir, ask Dhananjay sir to please let her share the screen.
Okay, okay, madam. Okay.
Or otherwise, you can
Dhananjay sir.
share the PPT.
Yes, ma'am. Dhananjay sir is sharing, sir. Madam.
He is not sharing, ma'am. He is making madam co-host.
Okay then.
Ma'am, you are now co-host. You can share.
Okay. Because of this upper one, slideshow is
Screen mode, you can. It's visible, ma'am. It's just.
Yeah. Is it visible?
Yes, ma'am, it's visible.
Yeah, my slideshow portion is not visible.
Slideshow mode. It's not working.
Madam, make it in full screen mode.
Slideshow. Slideshow is not working.
Actually, this wait.
Ma'am, you need to press mic.
Cursor is not moving to the slideshow, I think.
That's the problem.
So you have shared the PPT with the
Ma'am,
department.
click
They can share.
F5. Tap on F5 also.
Rachna ma'am, you are having the PPT?
No, ma'am. I'm
Then
Not share PPT with anyone.
Yes, ma'am. Share.
yes, ma'am, share your PPT. We will share from here.
Okay.
Press F5, then start slideshow.
Not working either. Wait.
No need. You share the PPT with us, ma'am. We will share it.
Ma'am, send PPT.
Okay, wait. I'm
Share
sharing.
PPT.
I am sharing in WhatsApp. Okay. Where should I send?
In my WhatsApp, ma'am.
In whose? It's 917003.
Yes, ma'am.
No, no, next. Yes, yes. 7020.
7020.
7020.
Rachna ma'am, you need to stop share also.
Okay. I have stopped sharing.
Yes. Done, ma'am.
Has it come?
No,
Check,
ma'am.
ma'am. No, I have forwarded. Now it will come.
Yes, sir. Received, ma'am. Received. I have received, ma'am.
You received, no?
Yes.
Yeah. What happened all of a sudden?
Wait for 1 minute.
Or should I try it once more?
No, ma'am. We are sharing from here. We have received your PPT. No issues.
It will take 1 minute only, ma'am. Yes, sir. Ma'am, it is visible.
Yes, ma'am, it is visible.
Visible.
Should I start, ma'am?
Yes, ma'am. Yes, sir.
Okay. The topic of this research is kinetic Monte Carlo study of island formation on patterned surface with the inclusion of strain monomer diffusion with detachment. Actually, it is a computer simulation of making of thin film. Okay, next slide.
Next. Run the slide. Next.
Okay. I want to share my experience. I started with the experiment part of making thin film first. When I start with my research work, I'm very much interested on that. But, at that time I was having a baby. So giving too much time in lab was so much difficult for me. That why I was shifted to this computer simulation at that time. Now, too, I'm doing in my lab, I have a experimental approach as well as theoretical approach and this simulation work going on parallel. So when I started with this one, I found so there are some importance of this computer simulation first. Computer simulations are very useful as it is a combination of experimental, theoretical, and simulation studies to understand and fundamental nature of film growth. As we know that thin films are having so much of scope nowadays, too much advancement in the field of electronics. The size of our devices or our instruments are decreasing day by day. Their compatibility is increasing day by day. So next is, what happens? We can, in lab, we don't have the precise control over the growth parameters of the thin film. But when we are doing in computer, when we are making the programming by ourselves, we can have a precise control over the growth parameters, and the actual determination of observables is still be difficult, which are very difficult in experimental, but we can do it in computer simulation. See, what happened is now in experiment, we can have it's very difficult to give different temperatures, different flux, try with everything. So what I suggest is that if we start with the computer simulations for the same condition, for the same experiment, for same research, we will get the optimal conditions on which we can work in the lab. So the main theoretical tool of microscope theory are numerical simulations. For that, we use two models. One is kinetic Monte Carlo and another is molecular dynamics. Out of these two, I prefer to be using the kinetic Monte Carlo simulations. Next. Okay, as I told you that there are two models. One is kinetic Monte Carlo model and another one is molecular dynamics model. I want to see the similarities and dissimilarities between these two models. See, both of them work in the atomist process such as diffusion, such as monomer hooping, corner hooping, surface diffusion, atoms attachment, detachment, step edges, desorption, so on. Both deals with the dynamics of growth process. Okay, these are the similarities of both the models. But what is difference between them is the methodological point of view, they are different. In molecular dynamic model, what is done is the set of, we initially give the condition and the set of equations are solved. Actual problem is done. There is no scope of probability and there is no need of correct rates. But there is one disadvantage of molecular dynamics model. It requires, when the time scale is large, it cannot be addressed. Like femtosecond range is best for the molecular dynamic model. Next, please. Okay, now I'm going for molecular dynamics simulation, which I told you just now. What the molecular dynamics solution consists of? First, we initialize the system. Initialize the system means where are my atoms, what are its initial positions, what are its initial velocities. Then we use Newton's classical laws of classical laws to solve. We do the integration. Then we calculate the actual quantities. Then same thing after that means by solving of the classical Newtonian equation, we do the molecular dynamic part. Next, please. But in contrast, kinetic Monte Carlo simulation, which is a subset of Monte Carlo simulation, it is totally based on probabilistic simulation, where if something having the more rate, if something is having the more probability, then it is given the more rate and it will have occur more frequently. So the kinetic Monte Carlo simulation, it is totally based on pseudo random generator and the probability. It is, as the name suggests, in the kinetic. There is Monte Carlo simulations also, and there are kinetic Monte Carlo simulations also. The kinetic Monte Carlo simulations, they are time dependent, and it's time dependent means they are dependent on the frequencies. For this, what kind of algorithm I'm using is Bord's, Kalos, and Lebowitz algorithms. Next, please. Okay. See, kinetic Monte Carlo method, the one which is which I'm preferring to use, and I prefer others also to use in this research field, is the one, I told you the event which is having the more rate, is having the more probability. It is used on the basis of the pseudo-randomers. Input to the KMC algorithm, the method itself cannot predict. It means rate is what we have to give. It is not produced within the algorithms. The main idea behind KMC is there is an energy barriers between the states. There are time increment formulated. So it is very much related for the microscopic kinetics of the system. Next, please. Next. Okay, the general objective of the research in kinetic Monte Carlo is to enhance the material properties by studying various models of atomic process with pattern impurity, detachment, and strain monomer humidity. My specific objectives roam around to find the island, the size of the island that are formed on the thin film. What is the average island density on the thin film? To see the effect of relative width distribution and to compare the average island size. Please. Okay. Now going forward towards the methodology of the research, we use the simplest model as used by Saito and Hein. Atoms are depositing on a surface cubic lattice with solid on solid restriction. There is no vacancy, no overhangs. Atoms are deposited randomly with the deposition rate F monolayer per second. We assume atoms attached to impurity do not dissociate. And this whole programming, I encourage everyone to write the programming in C. Means the software which we are using is made by ourselves. Next, please. Okay. This is an overview of the program which we have written. So you can see the program on the right-hand side. And when the program runs, it comes like this. This is the overview of the programming. Next, please. And when the program runs, whatever is the data comes and set in the Excel sheet. Now we have directed all the information which is gathered from that goes in the Excel sheet. And from the Excel sheet, we get the data and we can play with the data to get the various parameters needed for the surface morphology. Okay. See, here I want to show you the atomic processes which are occurring in our research, like what are the first one diagram. You can see this is a big island. Big island. These are all the atoms. And for me, if the number of you can change it in your simulation also. For what we have taken the parameter is if the number of atoms are having the size greater than 10, then up to it will have some center mass, and up to this range it can attract all other monomers. Okay, so this center of mass, this becomes a big island, and this and up to this range they can attract the other monomer atoms towards this island. So this will increase the island size. You can see the one which is outside this island range, it is not attracted. Now on the right hand side, okay, on the right hand side, this is a preview of all the atomic processes which can occur in the thin film. Like first one, we can go to next. I will touch in detail now. Okay. Can we remove the barrier from the up to down side? Just pull it down. Okay. Back. Now see, this is actually what I'm starting with my research work now. See, so the first point is substrate initialization. While making a program, we make a matrix. A matrix represents the substrate of the thin film. So here, while I was writing a software, what I did is I make a matrix of 300 into 300. So that makes my substrate. Okay. Now it goes to the next part of that thing, that is impurity deposition. Now, see what is done in my the work is I allow the deposition of impurity, but the deposition is not random. It's not like wherever they want go and deposit. I have given the fixed allocation. Like if there is a proper gap of x equals to 30 and y equals to 30, and after each that gap, another impurity is getting deposited. In total, I allow 100 impurity get deposited. I want to see the effect of impurity in case of the like thin film. What happens if we are doing some impurity over there? Okay. Now see the third step. This is the update the rate, total rate calculation of the event. There are so many atomic processes going on. Like we can see the first atomic process is deposition. Then another one is monomer diffusion in X direction. Monomer is single atom diffusing in X direction. Another one is monomer diffusion along Y direction. Then H diffusion along X direction. S diffusion along Y direction. This is the corner diffusion along X direction. Corner diffusion along Y direction. Detachment of atom in X direction. Detachment of atom in Y direction. Strain monomer diffusion. Strain means when the island is big and it is within the range of that big island. And this is strain monomer diffusion in Y direction. So what we are going to do from the literature we will use and other parameters, we calculate the rate of each and every event. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 events in this programming. So out of these all 11 events, what we do, we calculate the total rate by adding all the rates. See, and then at a time, only one event is selected. Like if suppose monomer diffusion is selected, the atom which we are observing, it will diffuse along Y direction. If another event is selected, whatever gets selected, the same thing will be propagated. Okay. Now after that, see in the starting when the substrate initializing, I am keeping all the elements to be 0. 0 indicates that there is no atom. And when the program runs, after that we can see, because I said 300 into 300 lattice was taken, it depends on how much coverage we want. If I want 0.1 coverage to be done, it means 99,000 atoms has to be deposited. So where the first atom will go and sit, there 1 will be written. And where this another atom will go and sit, that 2 will be written. So in this way, in a matrix which is visible to us in our notepad, we can see wherever which atom has gone and where it has been located. After that, the counter will learn. Updating list means what there is while making the program, we will calculate the number of atoms having single bond, number of atoms having double bond, triple bond, then how many of them have done monomer diffusion in X direction, how many of them have done monomer diffusion in Y direction, how many of them have detachment, all the things is over there. The list will be get updated. If this number is less than 9,000, as I have taken the coverage to be 0.1 of 300 into 300 matrix, what will happen? If this coverage is less than 9,000, then it will again go and again that atom will be doing one of these events. This will continue till all the atoms, till the SN max comes. So this is, if that condition satisfied, that will be our final configuration. Next. See, this is the rate. I told you that according to rate, the event will get selected. So in kinetic Monte Carlo simulation, we work on the random number generator. This works on a random number generator. And what number has to be generated? It is between 0 and the total rate. Total rate means rate of deposition plus rate of monomer diffusion, whatever are all the 11 events, whatever I have taken, the sum of all the rates will be done. In the beginning, QK value is taken to be 0. I equals to 1 means the first loop will run. I is initialized, this I value over in the third block is given 1, event 1. So now my total rate will be the rate of deposition only, the first one event, because QK is 0 and this Q1 means rate of deposition. So if this QK is greater than equals to random number which is generated, then it's less than my QK, means rate of deposition, then event 1, the first event will be selected, that the deposition of that atom will take place. So, okay, that will be taking place. But if it is not, then what will happen? I will become this, and value of I will become more. So what will be QK? QK will become rate of deposition plus rate of monomer diffusion, the sum of these two. Again, that random number which is generated will check with this rate. If this comes to be true, now event 2 means the atom will go to the monomer diffusion is X direction. In same way, in third, QK total rate will become rate of deposition plus rate of monomer diffusion plus rate of monomer diffusion in Y direction. So in this way, what will happen? One of the event is selected for the one atom. Okay, what process will going on? Next. As is based on computer simulation, so many block diagrams. Now see, nth atom from an event means I'm checking for only any one atom of the event. I will check the neighboring bond check. How many bonds? If there is no, then it is a monomer. If it is a monomer, I'm going to check whether it is a strain monomer or not. Strain means if it is in the range of a big island with the size of more than 10 atoms or not. So two different listing will be there. If it is a monomer, then either it is near the big island or it is away from the big island. To this kind of one listing will be done. If there is a single bond, one neighbor, okay, if there is single bond, it will take, if detachment takes place, yes, then another listing will be done that this single bond, this has one formed from the atom which has detached from somewhere. If no, then it will be listed under single bond. Similarly, if it will check bond, the counter will check where how many bonds are there. If there are 2 bonds, N2 and N3, again, it will check whether the atom has come from detachment or not. If it has come from detachment, it will be listed under D double bond. If it has not from the detachment, then it will be only double bond. Similarly, 3-way. And in 4 neighbors, N2, N3, N4, N5, it is only possible when the extreme deposition is taking place. In my case, I am taking the I have taken the 0.1 coverage, so it will not be possible. So H corner count will take place, and all the lists will be updated. You know, how many are of single bond, how many are from double bond, triple bond, or 4 bonds, and whether it is near the it is like near to the strained big island or not. Okay, the concept of center of mass will play a role over here. Next. Next, please. Okay. Now, see, for the sake of clarity or what, I have assumed 3 kinds of models. You know, while making the thin film, by using computer simulation, what is done only in the first case, the model, what is model 1 for me, it only consists of the pattern impurity, you know, means impurity means only impurity, pattern impurity is there, and simple only first 7, 8 that are allowed. In my model to consist of pattern impurity is there, but in this case detachment is also allowed. And the third model which I'm going to consider is, it's a pattern impurity with the inclusion of stone monomer, means strained monomers can move and detach also. So when I do, we can see the first model first. In case of first model, can I see the temperature upside? Side? Okay, if it is not visible, see, remove it. I will discuss. Okay, now go back. Go back once. This is very important concept. The upper portion. Remove the upper portion. First of all, what is it? It is, you know, after running the program and see what we have made, what kind of figure is coming. You can see A, B, C, D, E, F. This is model 1 where only the pattern impurity is there. The first one is for very low flux. It is 0.004 monolayer per second. The second one is for 0.02 monolayer per second. The third one is 0.04 monolayer per second. Fourth one, 0.08 monolayer per second. Then 0.1 monolayer per second. And the last one is 0.3 monolayer per second. So what I want to say is that while going from A to F, my flux is increasing. Okay, there is an increase in flux. So in the beginning, when the flux was very low, that is 0.004 monolayer per second, we can see the number of islands are around this black dot is for impurity. You know, you can see if there are 100 impurities, 100 islands will form. So what we can see is that it acts as a nucleation size, but the whatever is over here, you know, we can see the island is it is not of perfect shape, means square shape. Okay, as the flux is increased to 0.02 monolayer per second, again we can see there is little bit, you know, square, little bit correctness in the square shape. Further increase when it becomes 0.04 monolayer per second, we can see here there is one extra island formation is taking place, and there is no impurity within it. Means from here, from this flux, what happens is with like this only nucleation sites island were forming before. Now the extra island has also started forming. Okay, this island formation increases with the increase in the flux, which we can see in F. Have you seen? The island size is decreased and number of extra island without any nucleation site has increased. This is my first. Now going to the second model. In this second model, detachment is allowed. Atoms can detach from one island and go to another island. In that case, what is the difference is? So I'm going back to the first model first. We can see that in this one, the best one is the second one figure. It means my optimal condition is 0.02 molecular layer per second. So when we are doing the experiment, so we get an idea that this much will be my optimal value. So I can do my experiment around this flux value. Okay? This is called my optimal flux, at which square shaped and proper shaped number that's island formation takes place. That will act as a quantum dots, and the significance of quantum dots is all known to us. Going to the second model, in this model, detachment is also allowed. So when the detachment is allowed, we can see that the formation of island, as there is an increase in flux, when that this detachment process is allowed for the atoms, what happens is that when there is a cluster is too big, then the atoms will come out from the one where there is a conversion, and it will go to the one where the proper square shaped islands are formed. So this kind of pattern is observed. If I will compare F and R, okay, we can see that in case of F, when there is only impurity was present, the island size was little less, okay, and irregular. It is comparatively more bigger in size for the same flux, okay. And now for the third model is strain monomer hooping, means this one the one more parameter is taken into account, that is strain monomer hooping. Now what we will see is that because of the strain monomer hooping, in this also we can see that optimal flux is at 0.02 mono. This one is U. For all the three cases, for all the three models, optimal flux comes out to be 0.02 monolayer per second. As beyond this, the island size is increasing ununiformly. We want, what kind of island we want? We want square shaped, equal sized, okay. So which one will be the best? That will be U. So for all the three models, whatever I'm saying, this 0.021 will be my optimal flux. Okay. Now if I will compare any, like if I will compare E, Q, and X, if I want to compare, what I can see is that in third case, when the strain is taken into account, in that case, more uniform, okay, and comparison I'm talking about, in comparison, more uniform island formation is taking place. So this strain, E strain, is playing a role over here. Next one. Okay, going to this average island size versus flux at temperature T20 Kelvin. Okay, see the average island size due to model 1 and model 2 is almost same, but for model 3 its value is comparatively less. Okay, in the beginning we can see these red dots. The red dots are for detachment and strain. That is, I'm looking for the one lower flux. Okay, so I want to say that average island size due to model 1 and model 2 is almost same, but for model 3 its value is comparatively less. This means at lower flux value there is no significant effect on the average island size due to detachment, but because of strain monomer hooping there is improvement in size ordering. at, okay, this one is clear. So it means that if we will take into this account the strain, detachment and strain into account, my average island size is going to be more better. Now, after this one, lower one, if the temperature is increased, what happens? We can see the average island size. Look at this one, model 1. Average island size is very less, means so many number of islands are formed. And in case of this detachment one, black one, the upper one most, average island size is bigger than that of strain. Okay, so the red one is in between. Red one is in between one, the middle one, the third model which I am used. So which one model will be the best in this case? According to me, the best one will be, again, while taking the strain, when I'm considering the strain model over here, the lower flux in the lower one, average island size is almost constant, and at the higher one, it's decreasing in the same way as that of, as the temperature is increased, detachment increases at the rate in which, so because of the strain, more size ordering is taking place. Now next. See, average island density. We can see even at low flux values, the island number could not be less than 100, which result in the constancy of the average island density and size. The effect of detachment on the average island density begins to appear at the flux of 0.02 monolayer per second. On further increasing the flux value, the average island density increases due to detachment, model 2, but the value of average island density due to detachment is less than without the detachment model, that is model 1. This is due to the fact that at large flux values, the coalescence and aggregation of island takes place due to the detachment, which results in the formation of larger island, hence giving the smaller value of average island density. Next. Okay. This is my relative width distribution for T equals to 28. See what that relative width distribution gives. The smaller the value of the relative width distribution, the smaller fluctuations are in the island size, and better the size distribution is for that thin film application. Okay, so what happens now? We can see our third model. There is less variation. It means there is less variation in the islands. Almost all are having the same size. Thus, the flux of 0.02 monolayer per second is the optimal flux at the temperature 280 Kelvin, because almost equally sized islands are observed at this flux. At this flux, the islands are nearly of equal size and square in shape. Hence, the pattern impurity cases plays an important role to obtain nearly equally sized quantum dots. At high flux, the islands are nucleated randomly, and we get many extra islands at a place other than the impurity nucleating island, which yields the larger value of W. We can see that over here when the flux has much more. In the previous one also, we have seen many extra islands have formed. So this value is high just because of the extra island that has formed. This implies that more uniform islands are formed in model 3, showing more size ordering in that case. Next. Okay. Now, island size distribution for flux 0.02 and 0.04. Now see, the first one, this black one, we can see, just look at the green one first. This is model 3. This green one dots, detachment and strain, where it is with. So what we will find that, see, like for one value, the number of islands are very high. It means in this case, the detachment and strain model case, more size ordering is there, more perfect shape order, like more maximum islands are having the same size in comparison to the one with the pattern impurity and including detachment. Now, if we will compare 3, when there is a pattern impurity, the peak is less. And when we include detachment, peak has increased a little bit. And when we increase strain with that, the peak has further increased. It means that like Iceland becomes more uniform, more than when we take into account detachment, and it is further increased by using the detachment and strain case. Now, when we increase the flux, the increase in flux, we can see the peak has gone more up. No, it's like this is 5, this is up to 4, so it's like not up, value is less. Okay, when the flux has increased, the average island size has decreased. This can be viewed, from that atom diagrams which I've shown before. Okay, the same pattern is observed over here also. The next one. Okay, this one is for Iceland size distribution for temperature 280 Kelvin for different flux. Now they see the flux has further increased to 0.08 and that is 0.3. So what we find is that when the flux has increased, the number of islands formed are too many over here. Okay, and they are not having the same size distribution, random size, small, then a little bit big. So what happens is there is too much of variation. So what we can see is that optimal flux value is not constant every time. It depends on temperature. It depends on temperature what will be the optimal flux. So over here 0.08 also same pattern we can see. The green one is detachment and strain model 3. Over here this is having the highest peak, means it is having the maximum size ordering, but the size ordering, see, it's coming to the peak is coming near to 4. It means the average islands distribution is decreasing with the flux. Next. Now, second part of the this computer simulation. This is, it's visible from the diagram. This side, on my right hand side, it's like flux. You can see while going down, flux is increasing, and this side is temperature. So at temperature 220 Kelvin and very low flux 0.004 monolayer per second, this kind of islands are formed. When temperature is increased, we can see more uniform and more nucleated islands are formed. So for this 0.004 monolayer per second, which one is my optimal temperature? Which means where the more best island formation is taking place. The best formation is taking place at 280. You can see this is over here, 280 Kelvin, more maximum. There is zigzag up and down. So in comparison to other parameters, at 280 Kelvin, more organized pattern is formed. As there is increase in flux, 0.06. Okay. Again, in the low temperature, island distribution seems like to be that. And with the increase in temperature, we can see the more uniformity. But over here, where is the optimal one formed? It's again at T equals to 280. This is by optimal temperature. Optimal temperature is the temperature where the not perfect square set, but maximum, like in comparison to other. If I have to see the correct data, then I have to take the very less variation in this temperature. We have taken it for 150 temperatures and 150. But while showing over here, I have taken only 6 values of flux and only 6 values of variation of temperature. Okay. Now I'm showing it for a little bit more, flux of 0.02. And when the flux increases to 0.02, its value is going towards 300 Kelvin. We can see this value. Go to next one. Optimal flux is changing with optimal temperature is changing with the flux value. Yeah. When flux is 0.04, again it is the maximum, the one is that the optimal temperature seems to be 300 Kelvin. When the flux is 0.08, then it is 300. And when it is 0.3, optimal is 320 Kelvin. So what we can see is that when there is increase in temperature, okay, the islands are becoming more uniform, but further increase in temperature make it disordered. Okay, like from 300 to them over here. As there is increase in flux, you can see island number are increasing. Just look at the A4, A5 and A6. When temperature is T20, the islands are increasing. Same pattern we can observe in 300 Kelvin. Okay, but it is means in the small temperature range, it's more visible. And when the temperature is increasing, we can see 300 last one. When the flux is 0.3, the extra island formation is started taking place. Okay. Next one. Before this, yeah. Okay. Now effect on the relative weight distribution. Just before I told you that versus flux, relative weight distribution is when the value is low, they are having the quantum, the formation of this islands are more uniform. So we can see that when the temperature, have a look, it is lowest for the 300 Kelvin. Different flux have the different lowest. For the black one, which one seems to be lowest? The black one lowest is the first one. For red one also, the first one is the lowest. For blue one, we can see this, it's going down, and then again it's going up. It means after optimal flux value, its value is again relative distribution, means the size ordering is getting disturbed. Okay. For pink one, what is observed from this graph is that, like in the previous case, what we've seen, optimal temperature used to be constant for different fluxes. But over here, for different flux, the optimal temperature is not constant. The optimal temperature, it depends on the value of flux, and it's like in the beginning, as the flux is increasing, optimal value is also increasing up to a point. Okay, side by side, two graphs are shown to show you to do the comparison work. Okay, in this right hand side one, what we can see is this relative weight distribution. I'm again saying the relative weight distribution, if its value is low, it means that there is less variation in the island size. If this value is high, it means there is much variation in the island size. So I can show you that. You can see in the beginning, all of them are having high values, and they all are coming down. Okay, so at 280, have a look. Maximum of them having the lowest value over here. This green one. Okay, so this gives you the optimal temperature, and this gives you the optimal flux. So by knowing this optimal temperature and optimal flux, when we do it in lab, we find out the various parameters by doing the computer simulation, and by using the optimal conditions, we do it in lab, and then we come we study the results which we are getting from the computer simulation and the result which we are getting from the experimental one. For the experimental, what we use is for the same case, what we are using in the lab means in both the same, we are giving the same conditions and everything. That is the molecular beam epitaxy. Okay. Next one. Okay. Island size distribution versus island size for flux 0.3 monolayer per second. See, when the temperature is less, this is for very high monolayer. We can show in the last that the number of island formation is too big. So what is clear is, for when the temperature was T equal to 220 Kelvin, the average island was having a fixed number. 50 means almost equal size atoms were there. But when the temperature starts rising, when temperature goes from T equals to 220 to T equals to 240, what happens? Small, relatively small. Island size is getting smaller and they are becoming more uniform. Means now all are having the same size. You can look at this blue one, T equals to 300 Kelvin. You know, island size and island size distribution. So they are almost all are having the same size. Next one. Next one, please. Now this is for very low flux value. Okay, the island size distribution for a very small flux value, that is 0.004 monolayer per second, and that is also for different temperatures. And we can see that even when the this flux value is very, very small, 0.0404 monolayer per second, the islands are not uniformed. We can see it's randomly scattered. The scattered view is the scattered form of the island, different size and different numbers. Next one, please. So what are the various result? What we got is effect of temperature and flux on island morphology, average island size, average island density, and island size distribution and relative distribution on pattern impurity substrate with the inclusion of strain monomer hooping, including detachment of single bond. So what we notice is that equally sized square shape island are formed at flux of 0.02 monolayer per second. Okay. When we include the strain monomer diffusion, the more size ordering is there. It means more perfect resolution. That is good for our experimental purpose. At low temperature, many unequal islands were formed. Uniform size islands are formed at a certain value of temperature, which we call optimal temperature. Optimal temperature value is increasing with the increase in flux. In my graph, maximum height corresponding to maximum value of island size, and at optimal temperature, peak is minimum. It means that more uniform islands are formed, showing more size ordering. Next. This is the result of one model which I have shown. In this case, the model which we have used, impurities are given a fixed positions. Now what we are doing is we are allowing the impurity move. This already done. We have modeled the crystal growth by considering the mobility of impurity atoms. We have seen the results, what will happen to all these morphologies, island morphology, when the impurities are allowed to move. And we have also modeled the diffusion of, in the over here, the one which is forming the bond with the impurities are not allowed to move. Now we have made another model where atoms which are forming a single bond with the impurities, they are allowed to diffuse. We are working on the mobility of dimer and trimer on the substrate, the detachment of dimer and trimer from the island. This version we are trying to include in our flowchart. We are making a programming for that. That's all. Thank you.
Thank you so much, ma'am.
Yeah.
So,
And see, this thin film is as important in, it's coming under the physical chemistry portion, and this is as important. It's for the new one, it seems to be a little tricky, but it's very important for the current progress in electronics and optical and semiconductor devices. The whatever growth is done in the computer evaluation, everything, That is all because of these developments.
Very nice and significant lecture, madam. This must enrich our student and scholar regarding the same. Now, session is open for question answers. Any question you can write or drop in chat box, or you can unmute yourself and ask directly. Write your question in chat box of YouTube as well as in Zoom also.
I was planning to show the atomic process also. It was in over there. Okay, it's showing how the atoms moves, everything over there. But ideally my laptop doesn't work properly.
It is not working.
It becomes more, when we see, it becomes more.
Okay.
Any questions?
Any questions from participants? Abhishek sir?
I'm asking something in the chat box. Someone typing, ma'am. Someone typing. Wait for a minute.
No need to write. You can unmute yourself and ask directly.
If no question, we can proceed for further.
No question. Can I leave now?
Yes, madam.
Thank you so much, ma'am.
Thank you, madam, for a nice presentation.
Very nice and full of information, ma'am. And I think it must enrich our scholars, students, and they should ask a question regarding the same very nice topic and very relevant topic. Nice to have you with us, ma'am.
Thank you, ma'am.
Thank you. Thank you so much for joining us, ma'am. Abhishek sir, over to you.
Now, I'd like to invite Dr. Bilaspur sir. Sir, please brief background of Madam sir.
Now, Dr. Ananya Baksi, madam, is there? Madam, unmute yourself.
Can you hear me?
Yes, madam. Yes, madam.
Good afternoon, ma'am.
Good afternoon, everyone.
Ananya, ma'am.
Good afternoon.
How are you, ma'am? You have to wait long for your session and your lecture.
Should I share the
Yes,
screen?
madam, I'm giving a brief about you.
Proceeding further, I would like to invite Dr. Milan Hat to introduce Dr. Ananya Baksi, ma'am. Sir, please.
Thank you, madam. Dr. Ananya Baksi, madam, fascinated by the idea of research and especially in terms of nanotechnology during her MSc in Indian Institute of Kharagpur. She joined P. Pradeep Research Group in 2011 to continue her research career in physical chemistry. She received her PhD in 2015 from IIT Madras. Later, he selected as an institute postdoctoral fellow, followed by working as a postdoctoral researcher in the Institute of Nanotechnology, KIT, Germany, with Horst Hahn and Professor Manfred M. Krebs. Afterward, she moved to TU Dortmund, Germany to work with Professor Guido Kleber. Currently, she is an assistant professor in the Department of Chemistry in Jadavpur University. Her research centers around various types of nanomaterials in condense and in gas phase. Her principal focus in mass spectrometry of materials. Now, I will invite Dr. Ananya Baksi, madam, to deliver her lecture.
Thank you for your introduction.
Thank
I
you, madam.
don't have the access to share the screen.
Uh,
Now you are.
Ma'am, now you are able to share your screen. You are a co-host.
Can you see my screen?
No, ma'am, it is not visible.
yes, madam.
Visible now?
Yes, yes. Please make it in full screen mode.
Yeah, I did. I think there is some gap between the.
Yes, yes, yes. Full screen mode now.
Is it moving? Like the slide
Yes,
changed?
yes, yes, yes.
Okay. Thank you again to the organizers for inviting me for this prestigious lecture. As Professor Height already introduced, I am an assistant professor in Kadavpur University. So today I will not take so much time of yours. I will try to finish in time. And I'm going to talk about how metals affect our lives. So I would like to start by asking you a question. Is rice good for us? Most of the health conscious people will say, no, rice isn't because it's full of carb and we should consume it less. But we know from our ancient times that rice has many medicinal property because it contains a lot of minerals, some vitamins. So that is it's a staple food across the globe. So it's a question whether it's really good for us or not. So let me tell you a story. So there is a village in West Bengal. It's called Purulia district. In the Purulia district, so there are tribal people live there, and whenever they have stomach upset, they eat a specific variety of rice, and they get cured. So there must be something in the rice that is helping them to fight against the stomach upset. So, renowned rice scientist, Professor Dr. Deval Dev, he was interested and he tried to find out what could be the reason for that, and he approached us that what could be the ingredient present in the rice that is actually having this kind of property. So, this is how actually the Hindu covered the article that silver is being cultivated in the field, but that's not the case. But what we found that there's a specific rice variety called Garib Shal. It can actually accumulate silver in its rice grain. Now, in that region, there are several type of rice varieties are grown, and we found that specific variety that called Garib Shal, it actually can accumulate up to 15 milligram of silver per kilogram of rice. So that's already a huge number. But if we want to know that how this rice is being transported from the, like what is the source of silver in the rice, then we have to do some experiment in the controlled environment, like in the laboratory condition. So what we have done is we have mimicked the soil condition. So we knew that there is a little bit of silver that can be present in the Purulia district soil, although India has no silver mine, but there is little bit of silver is present throughout. And so we enriched our laboratory soil with silver a little bit higher the concentration than it is present in the normal field, and then we grew a rice plant in different seasons, and then cultivated different parts of the rice of the plant, and then digested it, and then measured inductively coupled plasma mass spectrometry. So that is called ICP-MS. So that gives you a quantitative information about how much metal is present in that sample. So if I just show you a pictorial representation, so we had very less amount of silver in the soil, but the enrichment happened in the root and in the rice grain. So actually, it's bioamplifying the amount of silver that is present in the soil to the rice. So it was about more than 10 times or close to 100 times enhancement was there. We also wanted to know that what will happen if we polish the rice, or at what position of the rice grain this silver was actually present. So we did a secondary ion spectrometry imaging, where you can actually selectively image silver throughout the depth of the rice grain. And we found that this silver was present only on the outer layer. So this is the part that's called alluron. It's normally when we use polished rice, that's what we all prefer. So we remove this part. So most of the nutrients part of rice actually stays in that layer. So if we remove that part, then we lose all the good activities. So one thing is clear, that plants can transport metals through their cultivation from the soil to the grain. So this is a way metal can come into our food chain. So silver is a good thing, but it's not always that all metals are good for us. There are heavy metals that can be contaminating our food chain in the same way. Now, what would be the other source of metals in our food? So throughout the globe, we all use metal vessel for cooking. So here is an example, because I'm going with silver, I'm showing you an example for silver vessel. No one cooks rice in silver vessel, of course, but not everyone has the opportunity to access Garib Sal rice. So as an alternative, you can cook your rice in a silver vessel, and actually higher amount of silver can be etched from the silver vessel to your rice while cooking. So silver so rice can accumulate metal while cooking also. So we had a lot of silver coming in the solution in the rice. Now, this was done with pure water, but none of us cook in pure water. So we have tap water that contains a lot of chloride, carbonate, and if you add those salts separately to the water, the amount of silver was very high. So it was about 21 ppm compared to 1.5 ppm in regular water. So huge amount of silver can come to your rice. And if you increase the cooking time, it will the amount will increase for sure. And it will depend on if the rice variety is polished or not. We have taken several rice varieties that were available in the market and then checked what are the different metals present in those rice, and then actually found that one of these specific rice was actually etching more silver. So we have gone through with that specific rice variety and found that with time it can accumulate a 1.5 ppm of silver or so. So now, if all the silvers are coming to rice, then what happens to the vessel? So we could not really take the whole vessel and put it under electron microscope. So alternatively, what we have done is we have taken a silver foil and then did the same process in a glass beaker, and then check the silver foil under scanning electron microscope. If you see that before cooking it was a smooth surface, and if you keep it in water and then heat it, nothing happens. But as soon as you cook rice one time, you can see that lot of rough surface has generated. That means this part already lost some amount of silver from it. And if you have carbonate in the solution, then this roughness was even more. So does this rice actually helps in antimicrobial activity or not? To check that, we have done these live and dead experiments, and we found that about 500 ppb of silver was enough for this antimicrobial activity. Now, of course, it happens with same way with any other metals. We all know about aluminium. What happens if you consume a lot of aluminium? And aluminium, if we do this same experiment in aluminum version, lot and lot aluminium comes in the rice. Now people are going towards a better alternative, and they think that copper could be a better alternative, but is it really any better? So acceptable limit of copper ion in water is about 1.3 milligram per liter. So that is 1300 ppm or so. So I'm showing you here that even if you cook rice in copper vessel, then you can get up to 9000 ppm of copper in rice. So too much of any good thing is also not good for the body. We could actually image copper from here. We could detect it through EDAX analysis. Now, what are the other ways metals can come to our food chain? So we all know that groundwater could be contaminated with heavy metal, and Punjab is one of the state which is heavily contaminated with uranium. So 30% of the groundwater is actually contaminated with uranium. And uranium has a lot of causes lot of health hazards, like causing cancers. And there are there is a village where highest number of people are actually percentage of highest number of people are actually having cancer. So that's called a cancer village. So we wanted to know if we have water in, if we have, let's say, uranium in water, will that uranium be transferred to our while we are cooking or not? So what we have done is we didn't take any water from Punjab, so we have externally added uranium salt to water and then cook rice in it. And we found that the acceptable limit is 30 ppb, but the rice can have about 500 ppb of uranium in it. And if you have even more, then the rice becomes yellow in color, which is fluorescent under the UV light. So you can map the presence of uranium in different parts of the rice, and even we were able to see how it is present. And here it doesn't matter if you have a polished rice or unpolished rice, or you use different variety of rice. All rice varieties showed that higher amount of uranium, higher than the acceptable amount of uranium was present in the rice while cooking. And while it actually being absorbed or being attached to the rice, it starts replacing the essential elements like iron, manganese, copper, zinc, chromium. So after uranium being attached to rice, this metal gets depleted. So this is actually decreasing the nutrition value of the rice also. So we try to mimic the food culture of the area, and we selected a couple of vegetables in presence of salt and without salt. All of them had higher uranium concentration than the acceptable limit, but we got a mixed result. We could not really draw any kind of conclusion from there. So now we understand there are multiple ways that metal can come into the food chain. So we wanted to know that molecular interaction of metals with let's say food. So whatever material, whatever food we chose were mostly rice. So that is full of carbohydrates. So we thought, okay, let's start with carbohydrate and see how carbohydrates interacts with metals. So we did our we have done a very simple experiment. We took a glass beaker, we put a silver foil into it, and then the glass beaker was filled with glucose solution. And then we heated it in presence of a little bit of stirring. And then we monitored the water for silver concentration over time. And we found that with time, silver actually gets dissolved to water. So dissolution of silver happens. And we have about 1 ppm of silver within a couple of hours, and we can see that the mass of the foil was decreasing with time. So that much of silver was coming to the water. And this was also highlighted in Hindu, that we could dissolve silver using glucose water. Now, why this is actually coming to water? So there should be some stabilizing effect. So what we have done is we have taken the water aqueous solution and then measured their mass spectrum, and we found that there is a complex formation, that is that silver ions form a complex with glucose, and that is a stable complex. So whatever silver is coming out of the surface, it's actually getting bound to glucose immediately. So the kinetics is going this way. Now, depending on what kind of carbohydrate you are using, the amount of silver can vary in solution. So we had just kept on increasing the glucose in unit in the carbohydrate chain, and we found that maltotriose, that is a trimer of glucose kind of, so 3 glucose units are there. So that had the highest activity compared to glucose, and alpha series, that is a 6 times glucose unit, the cyclic carbohydrate. So they had lower efficiency for extracting silver in the solution. And those silver, to prove that those silvers were actually in ionic state, not at silver zero state, so we did an XPS study, and we found that those silver ions, that silver come as silver ions, which are actually forming the complex. Now, again, as I mentioned before, that if you add external salt to it, because most of our tap water contains a lot of carbonates, phosphate sometimes, so we added different salts like nitrates, sulfates, carbonate, phosphates, and we found that in presence of carbonate and phosphates, these are actually reduced by 3 or 4 times to fit the scale so that everything can be visible. And a very high amount of silver can be etched by this process. So it was about 5 to 6 time increase was there from pure glucose to carbonate and phosphate. And that amount was high enough to just add a little bit of sodium borohydride to the solution, and you get immediately silver nanoparticle. So we had, and that was confirmed by UV visible absorption spectroscopy, where you have the characteristic peak of silver nitrate at a silver nanoparticle at 400 nanometer. Now, everything should be driven by thermodynamics. So we wanted to know that what is actually driving this reaction. So the complex formation must be higher, it must be very stable. So the delta G should be very negative so that this reaction should happen. So we did isothermal titration calorimetric study. So what we have done is we have titrated glucose against silver nitrate, and then added carbonate and phosphate in controlled amount, and then did these ITC experiments. And we found that in all cases, the delta G value were negative. So the reactions are favorable. They should actually happen. But in presence of carbonate and phosphate, if you can see here, so the numbers, they are more negative. So they form much stable complex, so the amount of silver etching is more. So it follows a proper thermodynamics by this process. So I have shown you before that during this dissolution of metal from the metal surface to the solution, so there will be a lot of roughness that is happening on the surface. So this is an ACM image of the surface, where before and after the reaction, you can see that surface has become very rough, and this roughness was actually giving us a very good 10 to the power 8 orders of surface enhanced Raman spectroscopy, so ACRS activity. So we could get a very high value just by using a silver foil that was etched by glucose. So we have done a lot of experiments. So this is a table that is actually every reaction was done in triplicate and for 7 days, and the maximum concentration is reported here. And if you see this entry at the end, so we know that silver makes much stable complex with nitrogen containing ligand. So we have added urea to the water, and we found that if we add urea, that the amount of silver was much higher in combination with the glucose compared to pure urea or pure glucose. Now, so we understand that this could be a way that we could actually extract metals from their metallic state to solution. So this could be used as a metal extraction process. So, but for it to be a true extraction process, we have to have a way that we can increase the amount of dissolution. So we are looking for better alternative, right? So we are always going towards green and sustainable way. So we cannot use harmful chemical for dissolving these metals in the solution. So we use green solvents, so water, green chemical like glucose, and now we try to use another chemical in combination so that we could have a synergistic effect in presence of glucose and the other ligand, so that we have more amount of metal coming to the solution. So we have chosen a tripeptide glutathione for this case. So glutathione has sulfur in it, so thiol groups, so that has much more attraction towards silver ions. So we thought that if we use this in combination, so probably we will have more amount of dissolution. So that was actually seen. So we had about 50 times enhancement just by adding a little bit of glutathione in it. And even cyclodextrin, which was not so well extracting silver, in presence of glutathione, it was actually comparable with glucose. And here also we could figure out that a very stable silver glutathione and silver glutathione plus glucose complexation happen, and that drives the reaction towards more dissolution in the solution. So we tried to explore the possibility that why cyclodextrin is actually helping in such in this case. So we found that cyclodextrin has this bucket type of structure, so it can sit on the metal surface. So whatever metal is being extracted by the other ligands, it can come and sit on it and then etch out one by one and then encapsulate it inside. So it's actually taking out the product from the solution, and then so that we can have more and more amount of metal coming to the solution. So each of those species for silver, this is shown for silver, zinc, copper. In all the cases, we could see that cyclodextrin and these metal complexes were very stable and was visible in solution by mass spectrometry. So as here amount of silver was much more compared to the previous only glucose case, and glutathione is known to create silver nanoparticle and even a smaller nanoparticle, that a subatomic nanoparticle less than 1 nanometer size. So we thought that we have plenty of silver in solution now, so can we check with sodium borohydride? So now we have added sodium borohydride to it, and we expected that we'll see yellow color for silver nanoparticle, but it was not yellow in color, it was reddish brown, and the absorption was also not at 400, it was close to 450 nanometer. So that was not for silver nano pure, like bulk silver nanoparticle. So we found by mass spectrometry that this was a very interesting cluster, that was silver 20 cluster. So that means that nanoparticle had only 20 number of silver atoms in it, so that small. So now here, if we see that what happens to the silver foil, then we saw that there is this blade like of flaky structure that was observed by high resolution ACM that was present. And when we did XRD of it, we found that silver sulfide layered structure was forming by this process, and we confirmed it by Raman spectroscopy. And this is how this structure can be understood from this peaks can be understood from this structure. And silver is still noble. If we shift to copper, the amount of copper was so high that you can actually extract copper in bulk. You can extract copper in milligram scale from a copper vessel. You can see the color change. So here is an example of a lot of copper in solution. So it forming copper nanoparticle. And it is a photograph showing that how much copper was actually coming was being extracted, and so it was in milligram scale. Again, we could figure out the complex that was forming with copper, glutathione, and cyclodextrin. Now we can extract copper by this process, but when we were doing all these experiments, we could see that there is always some floating particle on the surface. And those floating particles were not actually soluble in any solvent, any acidic condition or basic condition. So that intrigued us, what could be those particles? We could not solve it. That what could be it? I'm showing you an example where this is glucose solution in copper vessel, and this is a Teflon coated magnetic pellet. That's everyone, I'm sure, has seen one of them. And this is how it happens after the reaction. So it's all floating on the surface. And when we tried to do the same experiment with gold, these flaky things were actually pink in color. And we saw for the very first time that there is some corrosion happening, excuse me, on the magnetic pellet itself. And when we put everything under UV light, we can see that this bright red fluorescent material was formed. And there is no way just glucose and copper can make, or just glucose and gold can make something fluorescent. So we thought that probably some gold carbon bond is forming, which is known to be fluorescent, and that does not actually correlate with all our findings that we had done before. Then we looked the magnetic pellet more carefully and found that this magnetic pellet cover, that was the Teflon coating, that was actually being destroyed in multiple parts. So you can see that this part came out, this part came out. So it was burning off. And then we took those particles and then measured Raman of it. And then we took pure Teflon for our as our standard, and all the peaks that were coming from the flex, that was exactly matching with Teflon peaks, and we could see a new peak that was forming these metal carbon bonds. So that actually gives us the answer that why this gold containing flake was fluorescent, because gold carbon bond is luminescent in nature. So, and we have also done XPS studies to confirm that how this copper is bonded to like Teflon. So this has a very diverse implication that we are degrading Teflon that is known to be non-reacting or non-corroding plastic. But with this simple experiment, that is just by boiling glucose water in it, you can actually degrade Teflon. So that was as simple as that. So if you now think about what is happening in our ocean, we are dumping so much of plastic in the ocean, and we have the similar situation. It's full of nutrition. You have a lot of waves, so that's helping in the storing process. So all these plastics can be degraded by this process and then create microplastic, and once the microplastic forms, you cannot remove it. So microplastic degradation can be understood by this process. And we actually were able to separate this material in milligram scale just by doing this experiment. And we found that, so we wanted to know the mechanism, why this is happening, what would be the actual reason for it. And we did some interesting experiment where we have measured the charge of the charge on the water, how much charge is being accumulated while it was stirring or while the reaction was happening. So we found that in presence in while we have Teflon beaker. Just excuse me for a moment. Sorry. So we found that because of this Teflon is non-conducting, so it was accumulating the charge and transferring that charge to water, and that charge was creating a tribochemical effect that was helping in degradation of this plastic in presence of this metals and the carbohydrate. And we were able to detect this fluorinated carbon species in solution by mass spectrometry. So all these species, those are actually fluorine containing species, and that that without any doubt proved that we were actually dissolving plastic also by this process in water. So we have like by unknowingly we opened a new area where we could actually take care of e-waste, and we can simultaneously degrade or simultaneously remove metal and plastic together from the system and then go for a and do it very sustainably. So I hope enjoyed the talk. So I thank the organizers again, all the funding agencies for funding our lab. And this is our lab members. So there are a couple of PhD and master students. And thank you all for your kind attention.
Thank you so much, ma'am, for your insightful deliberation, beautiful and wonderful talk for our participants. Now we just open the room for question answer session. I would like to request Dr. Rachna ma'am to please proceed further for the question answer session. If any questions are there in the chat box,
Dear
respected
yes, ma'am.
speaker.
Yes. Dear participants, if you have any question, kindly unmute yourself and ask directly. You can drop your question in chat box also. Abhishek sir, is there any
from the YouTube chat box also?
Yes, ma'am, we are checking, ma'am.
Abhishek sir and Milan sir, you can take the questions from YouTube chat box also. Thank you so much, ma'am. It was a wonderful session. And thank you for your precious time.
Madam, someone asking about nanoparticle or microparticle?
Abhishek, your voice is too low.
Hello?
Yes.
Hello? Madam, someone asking about microparticle and nanoparticle.
So in case of metals, we normally end up getting nanoparticles, but for the plastics, it will be microparticles.
Any more questions?
You can ask directly. Unmute yourself and ask. Ask the question.
Raise your hand, then you will be unmuted and you can ask the question directly to our expert. She'll interact with you directly.
I think no question.
To wait for 5 minutes more, ma'am.
Okay, ma'am. Okay.
2 to 5 minutes more.
Actually, this is not my exact research area currently. So I thought that this is for the, I expected this would be for the bachelor's and master students. So I tried to keep it as simple as possible.
It's wonderful, very nice and informative too.
Within 2 minutes, you can just deliver the vote of thanks if no questions are there. Milan sir, any questions are there from your side?
Lots of students should have the question because it's a very relevant topic.
Milan sir, your voice is not coming. It's mute.
Okay. No, madam, there is no question in the chat box.
Okay. Any question from our faculty members, from our faculty side? Okay, no issues. You can.
If no question, then we can proceed.
You can proceed further, Rachna ma'am.
Thank you, ma'am. So,
can I on my video?
After the whole energetic session, right? I'm audible now? Yes. I'm audible? Yes. Thank you.
Yes, ma'am.
After whole energetic session, we are now at the end of today's event. So, it is time for vote of thanks. I, Dr. Rashmi Verma, Head and Convener of the event, Head Department of Chemistry and Convener of it, of the event. I'm here for vote of thanks. So, respected dignitaries, esteemed speakers, participants, and organizers. I'm, I'm honored to propose the vote of thanks for this international e-seminar on recent advances in chemical sciences. First and foremost, I would like to thank our Honorable Vice Chancellor Sir for his support, our Registrar Sir Dr. Arjun Tiwari for his support, and our I would like to express my heartfelt gratitude to our keynote speakers and presenters for sharing their expertise and insight with us. Your contribution have enriched our understanding of the latest development in chemical science. So, in session one, Professor Sabriya Yusan gave his very informative lecture in innovation driving the future of chemistry. Second session begins with Dr. Jhuma Ganguly, with the topic is aromatic anchored sugar hydrogen. Third session is Dr. Rachna Ghimire, Associate Professor, Tribhuvan University. She talk about kinetic uh, Monte Carlo study of Iceland model. And last session is uh, the keynote speaker of last session is Dr. Ananya Baksi, and the topic is how metal affects our life. So all the four sessions are full of information. Proceeding further, to our participants, thank you for your active engagement and enthusiastic participation. Your question, comment, and interaction have added depth and value to our discussion. I would also like to acknowledge support of our uh, our collaborators, IUPAC GWB 2025, Association of Chemistry Teacher, Dr. Guru Muli sir, uh, uh, Indian Photobiology Society, especially President and Secretary President Dr. Chitranjan Sinha, and Treasurer Dr. Gauri Sankar Roy Mahapatra, without whom this event would not have been possible. As we conclude this e-seminar, I hope that knowledge, ideas, and connection we have gained will inspire us to continue exploring and advancing the field of chemical science. I would also extend my I thank to to team of ITBI, Dr. Saurabh Mitra sir, Dr. Ravi Tiwari sir, Dhananjay sir, for their technical support. I would also like to, and in bottom of my heart, I would also like to thank Dr. Jyoti Chatterjee Mitra madam for his support, and IQAC team for supporting for the organizing the seminar. And our all the thanks to Jyoti Chatterjee Mitra madam for supporting, and she gave lots of advice, and all the she present in all the sessions in this seminar. Thank you once again for your contribution to the event. Maybe it a stepping stone to further collaboration, innovation, and progress in our field. Thank you so much. Thank you, students, scholars, and participation once again. All the HOD of Dr. C.V. Raman University and Dean of Faculty Dr. A.K. Srivastava sir. Thank you, uh, whom directly and indirectly supported the event. Thank you.
Thank you so much, Dr. Rachna Verma, Madam, Head Department of Chemistry, for vote of thanks. With the permission of Co-Vice Chancellor, Madam Dr. Jyoti Chatterjee, Madam, can we proceed for National Anthem, Madam? Hello? Hello?
Ma'am?
Madam?
I think there is some technical issues. Abhishek sir, we can proceed for further.
Sir, I think technical issue, sir.
Yes, yes.
So please stand on your places for the national anthem to conclude the program, please.
Okay, ma'am. Okay.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you all for your quality participation.
Ma'am, it's
Thank
time
you,
to
madam.
take a group photo.
Okay. Let all the participants to switch on their videos. Other hosts,
Participant, unmute yourself. All the participants.
ask Dhananjay to unmute all the participants and just allow them to just switch on their videos. Group photograph for this event.
The video only.
Rina Nashini ma'am, you can switch on your video. Have the screenshot and end the session. सभी लोग अपना वीडियो ऑन कर लें, ग्रुप फोटोग्राफ हो रही है. सभी पार्टिसिपेंट्स अपने अपने वीडियो जरूर ऑन कर लें. I think now it's okay.
Yes, ma'am.
So thank you, Dhananjay, for continuous support.
Thank you, ma'am.
So thank you all, and wish you all a very best at all your endeavors for a better tomorrow. Thank you.
Thank you.
All the participants.
Thank you, ma'am.